Good morning, everyone. So I hope everybody is doing good. Yes. So I asked you two people to solve some questions in the previous gate. In the previous session. So I asked you two people to solve the classroom practice questions. So now let's see that classroom practice questions. We'll be winding this chapter number 8 and we'll start the chapter number 9 now. So let's have. See, yesterday we discussed about this failures, piping failure, and we discussed about quicksand condition also occurs when a trench is excavated below water table and made the excavation free of water. And condition number 3, if an excavation means made into clay stratum, see wherever you see the clay stratum underlain by the sand stratum, which is having artesian pressure, just simply you equate the upward and the downward, then you will be getting to know the depth of the excavation. And we have solved some questions also in previous gate. So these were the questions that we have solved yesterday. So now let's see the remaining things. You see. Yes. Come to these questions. We have been discussed about question number 1, question number 2, question number 3, and now coming to the question number 4. See the question number 4. See the question number 4. A soil layer of 1200 mm. A soil layer of 1200 mm. So the length or thickness of the soil is going to be 1.2 meter. Of grain specific gravity, what is meant by grain specific gravity? G value. Porosity 30% is subjected to an upward seepage head of 1.8, which means there is upward seepage. The head required to cause the flow is 1.8. Seepage head or hydraulic head or total head loss is 1.8. Find the depth of the coarse sand required above the soil to provide a factor of safety of 2 against the piping. So they are asking find the depth of the soil required to keep above the soil. See, there was some soil layer already whose length is going to be 1.2 meters. Whose length is going to be 1.2 meters. And now we are going to insert some more sand to provide a factor of safety of 2. See, for this point, let me look over here. What is the factor of safety? First of all, IC by I. Everybody listen. You know that IC does not change. And IC depends upon G, yes, is there, and porosity is there. But coming to the I, when does factor of safety increases? When I value decreases. When I value decreases, what is I? H by Z. I told you yesterday clearly, as an engineer, our main intention is to increase the factor of safety by reducing the hydraulic gradient. How come I reduce the hydraulic gradient? You say I can reduce the hydraulic gradient by increasing the length of seepage or not? Yes, that's what we are going to do. Find the depth of coarse sand required above the soil, which means you are increasing the length of soil mass. Assume that coarse sand has the same porosity and specific gravity as the soil, and that head loss in the sand is negligible. So no head loss in the sand. So now this is the question. So we need to find out the extra soil mass that we need to provide it. So now let's see this question. Remember these values, L value, G value, N, and head and factor of safety. Now, classroom practice question. Question number 4. Given details are The length of the specimen is 1200 mm, which means 1.2 meters. Specific gravity 2.65. Porosity 30%. Porosity is 30%. And apart from that, the soil is going to be having an upward seepage head of 1.8 meters. Then, what is the length of the coarse sand in order to provide a factor of safety of 2? So now you observe the meaning of this question is, you see, already this is a soil element. Already this is a soil element. And this soil element length is going to be how much? This soil element length is going to be 1.2 meters. 1.2 meters. And this is going to be subject to the upward seepage head of 1.8 meters. Now, I need to improve the factor of safety. You know the factor of safety is equals to IC by I. So if I want to increase the factor of safety to 2, if I want to increase the factor of safety to 2, then I have to reduce the I. If I want to reduce the I, then I have to increase the seepage level. So now what I am going to do is, I am going to provide one more layer on the top of this soil. So let's say this soil is going to be coarse sand. And what they mentioned is the coarse sand has the same specific gravity and porosity of the same soil mass. Okay. So now what happens over here? Then what is this length? This length is going to be, let's say it as X. Now you please tell me what is the total seepage length here? The total seepage length is going to be 1.2 plus X. So initially 1.2, now I am increasing it to some X percentage above that. So what is that X value? So you know that when the length of seepage increases, definitely, obviously, the factor of safety increases. So now let's see how to find out this value. You observe, first you find out the IC value. What is IC value? G minus 1 into 1 minus M. 2.65 minus 1 into 1 minus 0.3. So find out this IC value. The IC value is going to be 1 minus 0.3 into 2.65 minus 1. So which is going to be 1.155. 1.155. This is the IC value. Now, factor of safety is equals to, what is the factor of safety? 2. 2 is equals to 1.155 by I value. So what is I value? I means, we can write, yes, I is equals to H by Z. So I is equals to H by Z means now from here, H by Z is equals to 1.155 by 2. Yes. So what is H value here? 1.8. 1.8 by, what is the total Z value, please? What is the total Z value here? The total Z is going to be 1.2 plus X. So 1.2 plus X is equals to 1.155 by 2. So now you find out the X value. So 1.155 by 2, 1.8 by answer minus 1.2, which is going to be 1.92 meters if you round it to 2 decimals. 1.92 meters if you round it to 2 decimals. See, if I provide an excess length of this value of X value 1.92 meters, then I can provide a factor of safety is equals to 1. Factor of safety is equals to 1. Okay. So now, initially, if you observe, this is the question. So what they're asking is, if I want to increase the factor of safety, how to determine the, means how much amount of the length I required extra. For example, in this question, if I ask you, check whether the quicksand condition occurs or not with the initial length of soil. Now, B, check whether quick condition occurs or not with initial length of soil. What is the meaning of initial length of soil? Then seepage length is going to be Z is equals to 1.2 meters only. Okay. So now, as you know, factor of safety is equals to IC by I. Now, what is I value? H by Z. What is H? 1.8 by 1.2. So 1.8 by 1.2, 6362, so this is going to be 1.5. Then the factor of safety is equals to 1.155 by 1.5, which is going to be less than 1 or not? Yes. So soil will fail. You see, what I have done over here is I just checked whether the quick condition is going to be appeared or not with the initial length of seepage. What is the initial length of seepage? 1.2 meters. So if you go for just 1.2 meters, you see the factor of safety is going to be less than 1. See, I did not find out the total value, but you know that 1.15 by 1.5 is less than 1. So now, if I want to improve the factor of safety, you know that the only option is I should decrease. I will decrease when Z will increase. So when Z increases, I value decreases, then the factor of safety is going to be increases. So if I want to go for factor of safety of 2, how much length I have to provide is 1.92 meters. This is the question. Sir, we can solve it by upstream pressure is means upward pressure equals to downward pressure? No. See, they have mentioned the factor of safety, right? You observe over here, when they have mentioned the factor of safety, you have to consider those, yes or no? So factor of safety, this is not a critical condition. When critical condition occurs, then upward is equals to downward. See, when critical condition occurs, I am telling you maximum depth of excavation, critical condition upward and downward are going to be same. But here it is not going to be possible. So now let's see this question, question number. Just now I said Mr. Limbasia, the downward by upward is equals to 2. Is that okay, sir? No, here you have to take that submerged pressure, okay? Submerged pressure. See how I have got this one. You remember this one, right? How I got this equation? Have you remembered this equation? How I got? How I got that equation? The downward pressure, gamma dash into Z by gamma W into H. From this only I got this equation, right? Then why you want to go for again that equation? Do you know the gamma value here? Do you know the unit weight of the soil here? Did I mention any unit weight? Else again you have to find out G, E, and from that you have to find out the gamma. Is it necessary for you? Is it necessary for you? No. See, this is a high procedure. So that's the reason why we made this factor of safety from this condition to this condition, right? So it's better you apply directly factor of safety is equals to IC by I. IC is equals to I is quicksand condition. When IC is going to be less than I, then see, once quicksand condition occurs, that is a critical state. And less than that, definitely there is going to be failure. Now let's see the next question. See the question number 5 here. See this question number 5. If you observe, calculate the effective stress at the bottom of the silty clay shown in the figure and determine still how many days to complete this subject, sir. Sir, it will take time, sir. See, if you means I told you in every day of the class and every day people are asking still how many days it will complete. It will take time. Okay, it will take time. So you don't need to worry about the syllabus coverage and all. It will be completed. Okay. So forget about you are thinking like whether it is going to be completed or not. Don't worry, it will complete it. There is a lot of time and subjects are there. We know generally we used to start the long-term batches by this time only, which means that the first subject should start by now only, and we used to complete it at the end of the November. So you don't need to worry about that. Forget about when the subject is going to be completed. Look over how the subject is going to be understandable. And make sure whether you are going to get a 90 to 100%, means you are going to get maximum efficiency from this subject. Okay, so that's the one thing that you need to worry about. Okay, fine. So now you see this question number 5. In this question number 5, calculate the effective stress at the bottom of silty clay, which means they are asking here effective stress. Also determine the head above the ground level. Also determine the head above the ground level that would cause heaving at the base of silty clay. So you see, first of all, everybody, what is this? This is the water table or not? Yes or no? And this is a standpipe. When this is a standpipe, see, when the water level in the standpipe is more than the water table, then can I say this condition is nothing but artesian condition? Yes. See, the people who are asking me, sir, how to fix the artesian condition over here? You observe here clearly, when you insert the piezometer or bore well, this is the water table in this sand. This sand, this is going to be a confined aquifer, so unconfined aquifer. This is an unconfined aquifer because the top layer is going to be whom? Sand. And below silty clay, its permeability is very less, and then this is going to be a sand. This is a confined aquifer. Sir, how come you predict all these things, sir? Sir, I don't know anything. I don't know anything of this one. But what I do know is, if you observe here, I told you clearly, in the case of the bore well, if this is an artesian well, then the water level in the artesian well will rises more than this unconfined aquifer water table. See, you please go through the previous chapter. In the previous chapter also, where is that question? Yes. Okay. See, you see this in chapter number 7 also. You observe water table is at ground surface and sand in the water layer sand pipe. Water layer rises 2 meters above the ground surface, which means that is an artesian condition. So whenever the water level in the standpipe or borehole rises above the water table, that represents the artesian condition. So now come to the point. So now, sir, in this question number 1 is finding the effective stress. So that we can find out. But what is the meaning of this heaving, sir? When does heaving is going to occur, sir? I told you, sir, heaving at the base is nothing but effective stress is going to be 0. So the maximum for no heaving or at a critical condition, we know that effective stress should be 0. When effective stress is 0, then total stress is equals to, what is this? Artesian pressure. So now what I'm going to do is first I'll find out the effective stress, then we'll see that how to find out this that would cause. Also determine the head above the ground level. Head above the ground level, which means what about the head that should be present above the ground level to make sure heaving at the base of a silty clay. Let's go to these details. So this is details sand above unit weight gamma 18, below 20, and silty clay unit weight is 19. They have inserted the what is this artesian well in the case of the sand. So okay, so now you observe is classroom practice question 5. Question number 5. This is question number 4, and here it is going to be question number 5. So now this is a ground level, and there is a water table. There is a water table, and you know this layer is going to be sandy layer. Above gamma is 18 kilonewton per meter cube, and below gamma sat is equals to 20 kilonewton per meter cube. And then this layer is going to be silty clay, whose gamma sat is going to be 19 kilonewton per meter cube, and I want the effective stress at this condition. So here this sand is going to be there, and you see whatever the water level in this piezometer or standpipe. So normally already it has been raised up to 4 meters above the ground level, and beneath the 2 meters is above the water table. So totally above the water table, how much total height the water level rises in the standpipe? 6 meters. So this is again, this is going to be 2 meters, and this is going to be 4 meters. This is the given details. See, I can find out with our common sense, I can say all these things, because we know that, okay, this is a sand which is below the ground level. Is it going to be a confined or unconfined? This is unconfined, and here it is going to be silty clay. Beneath that, who is there? Sand. So this sand is going to be confined right over here. So then it is going to be, yes, this is going to be confined aquifer. So in the case of the confined aquifer, you see, I can say here directly one point, as water level in standpipe inserted in sandy layer rises above water table, sand is under Artesian condition. So when the sand is under Artesian condition, then what you need to do is simply find out the effective stress. What is the effective stress? Total stress minus pore water pressure. So you know that whenever it is an Artesian condition, then the pore water pressure becomes Artesian pressure. So find out the effective stress, please. What is the total stress equation? Find it right. Everybody, please find out the total stress at this point. What is the total stress? 18. See, in this 4 meters above, is there any soil mass? No. This 4 meters is a pressure exerted at the bottom. Okay. So what is the total unit weight here? 18. 18 into how many meters? 2 plus 20 into 2 plus 19 into 4 minus gamma W into 4 plus 2 plus 2 plus 4. Did they mention anything regarding to the gamma W over there? Let's have a look. So they did not mention anything regarding to the gamma W. So now let's take that gamma W as 9.81. So effective stress is equals to 8 into 36 plus 40 and 19 force 76 plus 40 plus 36 minus 10 into, you see, 4 plus 2 plus 2 plus 4, which is going to be 12. So then effective stress is equals to minus 120, which is going to be 32 kilopascals. So this is the value we got. This is the value we got. So this is simple. That's we can find out anywhere because we have done these questions similarly in the previous chapters. Now you see the next question. The next question is important here. What is the next question? Also determine the head above the ground level that would cause heaving at the base of silty clay. So yet means for not to cause heaving at the base of silty clay. For not to cause heaving at the base of silty clay, which means that is a failure condition or not. So whenever I say for no failure, I told you the maximum means effective stress is going to be 0. So what is the meaning of effective stress is going to be 0 here? What is the meaning of effective stress is going to be 0 here? So here if you see, for no heaving failure, effective stress should be 0. Effective stress should be 0. So for effective stress 0, see what is the initial effective stress I have? 32. Now I want to make sure effective stress 0. First I'll go with the logic, means basic, then I go for the logic also. Have a look once. So when effective stress is equals to 0, total stress is equals to Artesian pressure, which means total downward pressure is equals to total uplift pressure. Total uplift pressure. So what is the total downward pressure here? Already I have. What is this value? Please you tell me. So you please tell me over here. 36 plus 40 plus 76. 36. You see already I have find out this as a total stress, right? Whatever this is nothing but the total stress. So which is going to be 152 is equals to PA gamma W into HA. Then what is HA? 152 by 10, which is going to be 15.2 meters. So which means if the total level in the standpipe is going to be 15.2 meters, if the total level in the standpipe is going to be 15.2 meters, then you see whatever the total downward pressure over here, which means a total stress, whatever the total downward pressure is equals to total uplift pressure. That's the condition, right? What is the total downward? Total stress. What is the total upward? Uplift pressure. So whenever the HA is going to be 15.2, then the heaving condition is not going to be happen up to that point. If you go beyond that, then there is a heaving condition. So now you see, but they're asking about the head above the ground level. See, up to now. The head of water above ground level is equals to 15.2 minus, see already how many meters it was there? Already how many meters it was there total? the total, it was a total of 12 meters. So now if I rise this to 15.2 meters, which means how much extra height is going to be raised? 12. So which means 3.2 meters above ground level. If it rises extra, so then you are going to see the effective stress is going to be 0 and no heaving failure. Up to this point, no heaving failure. And if you go beyond that, if water level rises more than 3.2, heaving failure occurs. So the logic over here is okay. See, they're asking above the ground level, right? Yes. So above the ground level, give me a minute once. Yes. So that would cause, also determine the head above the ground level. Above the ground level means, you see, yes. So the total is going to be now, if you rise this water level to 15.2 meters up to ground level, what is this value? This is going to be 8 meters. Yes or no? So 8 meters, which is going to be 7.2 meters. So if the water level rises above the ground level by 7.2 meters, then the artesian condition is going to be happen. Effective stress 34. Hey, please go for that ray. Yes. We should not include it. They are asking above the ground level, not above the standpipe. So above the ground level means you have to take. See, the extra rise is going to be 3.2. Then the total rise above the ground level is going to be 7.2. So that's about this question. Sir, why did you take gamma W as a 10 when nothing is mentioned in the question? That's the reason why I told you yesterday. If it was an MCQ question, then you can go for the 10. If it was a numerical type question, then you can go for the 9.81. So you don't need to worry about those values. If they don't give anything, they will give you the range also. Okay, don't worry about that. Okay, fine. So now let's see the logic over here. The logic is, you know that question for you. So now the logic over here is, for effective stress is equals to 0, then the change in effective stress is going to be minus 32 kilopascals. I hope you understood the meaning of this one. For effective stress is going to be 0. See, what is initial effective stress? 32 kilopascals. And for no heaving failure, or up to no heaving failure, or up to critical condition, I can write this one also, up to critical condition, effective stress is equals to 0. So when effective stress is equals to 0, now if you observe, initially it is going to be 32 and finally it should be 0. Initially it is going to be 32, finally it should be 0. So now I can write a point for no heaving, then effective stress is equals to 0. Then what is the change in effective stress? Final 0 minus initial 32, which gives minus 32 kilopascals. So you know that delta sigma dash is equals to delta sigma minus delta U. Delta sigma minus delta U. And here this U is equals to minus delta PA. Yes. So now if you observe carefully, is there any change in the unit weight of the soil mass? You please observe over here. Throughout the soil, is the unit weight of the gamma changes? No. Is the unit weight of gamma sat changes? No. If the unit weight of gamma sat changes? No. Is there any rise of the water table? No. No change in the unit weight. This is the fourth time I am mentioning you when there is no change in unit weight, no change in gamma, then change in total stress is equals to 0. When change in total stress is equals to 0, the change in effective stress is equals to minus PA. Minus delta PA means minus delta HA is equals to minus 32. Minus delta HA is equals to minus 32, or as a minus 32 is equals to minus 10 into HA. Then, sorry, delta HA. Then what is delta HA? This is going to be 3.2 meters. So delta HA means the increase in the head, and above ground level, this is going to be 4 plus 3.2, which is going to be 7.2 meters. See, simply I understood one point over here as whenever there is no change in the unit weight, so heaving failure and piping failure. Piping failure occurs on the dams, heaving failures in the case of the excavations or the soil deposits. But both are going to be occurred due to quicksand condition. Once quicksand condition occurs, then only piping failure occurs. You please go through the notes once again. So now you observe over here, as there is no change in the unit weight of the soil, is there any change in the total stress? No. You please find out the total stress. If you find out the total stress remains same. Yes or no? But for no heaving failure, I have to make sure effective stress is going to be 0. I have to make sure effective stress is going to be 0. So then what is the change in effective stress? Initially it is 32, final it should be 0. So final minus initial minus 32. And the change in effective stress is equals to change in total stress minus change in artesian pressure. So as there is no change in the gamma, no change in the unit weight of the soil mass, so no change in the total stress. Then the change in effective stress is equals to minus delta PA. So minus 32 is equals to minus delta PA. What is delta PA? Gamma W into delta HA. So then the increase in the head, artesian head. If you see, if the water level rises into this point, above as 3.2 meters extra, then what is the total, please? Then the total is going to be 15.2. And above the ground level, this is the value. Above the ground level means, see, above ground level, this is the value, 4 plus 3.2, which is going to be 7.2 meters. That's it. See, what if gamma change? If there is a change in gamma, how the gamma is going to be changed, right? The gamma changes when either water table should rise or water table should fall. When there is a change in this water table only, then there is a change in the gamma. Then total stress is also going to be changed. Is this a question that you want to ask? What if gamma changes? And still some persons is asking okay, fine. So now, sir, by taking gamma W as 9.81, we get a 34 kilopascals. So 152 minus 1. So don't worry, my dear student. Actually, so they should have mentioned that gamma W as a 10. It should be mentioned over there. So you don't need to worry about that. Gate exam extend or not, sir? Arey Babu Dasu Nayak, this is 16th day, and almost in the 16 days, around 12 to 13 days, I told you that about the gate examination. It depends upon the IIT who is going to be held. We never know whether it is going to be extended or not. So don't worry about now. You please prepare for the examination. For concurrent aquifer, water level above ground level affects the effective stress. Yes, definitely. So now, let's see the next question, please. Look, I told you here Artesian condition. You please go through this point once again. You understand this point, Ray. Just don't ask me silly questions and don't make me to feel angry. Sir, what if it is a clay sand, sir? What if it is a something, sir? You please look over, sir, this point, sir. When the water level in the standpipe insert in sand layer rises above the water table, sir. You see this one, sir. What is this, sir? This is above the water table. See, I'll show you. Means whatever the PDF we have been discussed in the previous class also. Sir, somebody who are asking here, sir, you see this one, sir. Those who are asking, sir, what is this, sir? This is a groundwater table, sir. What is this, sir? Unconfirmed aquifer, sir. So they have given this as a sand, sir. And here this is also going to be sand, sir. By inserting the piezometer, where the water level is rising, sir? Is it rising? See, this is the ground level, right? And is it rising above the ground level or not? And forget about that. This is the water table, and the water level in the standpipe is rising above the water table, which means there's an Artesian condition. Whenever the water level in the standpipe inserted in the sand layer rises above the given water table or above the ground level also, that condition is known as Artesian condition, and that well is known as Artesian well, and that head is known as Artesian head, and that pressure is known as Artesian pressure. Now, Mr. Ravinder Reddy, sir, please explain GATE 1995 2 marks question of this chapters. How many times you will send the same question? I will look over that question. See, if I do explain each and every question in the classroom, it's not going to be possible. So I'll tell you what to do. Don't worry. Now, next question. So we have been discussed about question number 4 and 5. Now, question number 6. Question number 6. See, this question seems to be question number 6 and 7. Yes. This question seems to be bigger one, but it does not have any values. Figure shows a section of water-bearing sand strata located between two impermeable strata, so top and bottom. See, this is a figure above clay, and below clay. In between, this is a sand layer. So what they have mentioned is now there is a hydraulic gradient in the pervious layer causing a straight horizontal flow of water. So what is the flow over here? The flow is going to be horizontal flow. With a seepage velocity. What is the seepage velocity? Vs is equals to 6 into 10 to the power of minus 4. See, it requires the concepts of your chapter number 6 also. So seepage velocity Vs is equals to 6 into 10 to the power of minus 4 centimeters per second. Two piezometric tubes are inserted at point A and B. Now you see, everybody, here there is a horizontal seepage, and it has a seepage velocity of 6 into 10 to the power of minus 4 centimeters per second. Is it? Yes, 6 into 10 to the power of minus 4 centimeters per second. So now, Now you observe over here, they have been inserted are two piezometers. They have been inserted two piezometers over here, and these piezometers are going to be 14 meters apart. These piezometers are going to be 14 meters apart. So these are going to be the two piezometers, and the length between these two piezometers is going to be seepage length as 14 meters, and the water level, this HA, this water level is going to be 5 meters at A. And what is the water level? This HB they're asking. If the laboratory value of K is going to be 1.2 into 10 power of minus 3 centimeters per second, and porosity is 40%, and gamma sat is going to be 20. First, you find out the piezometer value at B, and then we discuss about the remaining things. And see, this is the next question. This is the next question. First, we'll solve about the HB value. Then we go for the remaining questions. Have a look now how to find out this HB value. So you please remember these values. Vs is equals to 6 into 10 to the power of minus 4, whereas K 1.2 into 10 to the power of minus. You observe. Now I don't draw everything. This is CRPQ question number 6. So now this is a sand layer, and there is a horizontal seepage. So they are inserting two piezometers at a point A and B, which is 14 meters apart. See, I am not discussing anything regarding to the clay over here because there is no seepage in the clay. So now they have inserted two piezometers. One is at A, other one is at B. So these are the two piezometers inserted. Now in this piezometer, whatever the level of water rises above the sandy layer, this value they have mentioned as HA. So this HA is 5 meters, and you know this water level and this value they mentioned as HB. So you know that whatever this line joining these two, this is nothing but the hydraulic gradient line, right? This is the hydraulic gradient line, and you know whatever the difference in the water levels is nothing but the hydraulic head or head loss. So if it is a starting point, that's a hydraulic head, and the ending point, that's a head loss. So this is the given question, and the details they mentioned is seepage velocity is going to be 6 into 10 power of minus 4 centimeters per second. K value is going to be 1.2 into 10 to the power of minus 3 centimeters per second, and porosity N is equals to 40%. So I hope these details are true. Okay, so here they mentioned gamma W, take it as 9.81. Now you observe question number 1. What is the first question I am asking you here? See, I am drawing this figure for better understanding of yourself. So you don't need to draw this one in the examination, because see, I have to go back and go forward. So that's the reason why I draw this figure, for making you understand. See, I want this value. Now, whatever we know is whenever there is a flow, see, they have given the seepage velocity, right? Then definitely can I use the velocity from Darcy, only one step. From Darcy, V is equals to Ki. Yes or no? And as we know, Vs is equals to V by N. Can we write V as a Vs into N? Vs into N is equals to K into I. What is I? H by L. So everybody have a look. From this condition itself, I got everything. Now you observe, does we have Vs? Yes. Does we have K? Yes. Does we have porosity? Yes. Does we have length? What is the length? Yes, 14. And what I can find out here is, if I can find out the H value, you know the HA, and if you remove the H value from the HA, then can't I find out the HB value? Yes. So the question is going to be too bigger, but I know they have given seepage velocity and permeability, then I can find out from Darcy the head. So now you please find out the head over here. So what is the Vs value? 6 into 10 power of minus 4 into what is N value? 0.4 is equals to 1.2 into 10 power of minus 3 into H by what is L value? 14. So now after solving all these things, you will be ending this H value as 2.8 meters. 2.8 meters. So now you see from figure, this HB is equals to HA minus H, or I can write H is equals to HA minus HB. Then what is HB? HB is equals to then HB is equals to 5 minus 2.8, which is going to be 2.2 meters. Are Mr. Anonymous, do we have any mind with you? V is equals to KIA. Is this the one that I said? Does V is equals to KIA? You please go through the notes once again. Yes, they have given in meters. Why? Why did you worry? See, this is in centimeters per second, and this is also in centimeters per second. Everything will get cancelled, right? This units will get cancelled with this units. So whatever this point for does not have any units, I took L as a 14 meters, then H will be now 2.8 meters. So this is a question number 1. Now in the question number 2, what they mentioned is there is an element, this element is a C. There is an element C in between over here. What is the resultant force per unit volume? See, they're asking, you see, determine the resultant body force on a soil element with unit volume. What is the meaning of that? Resultant force per unit volume in the vertical section C, midway between A and B. So you see, in this, this is going to be a small element C. And what is the type of seepage over here? Horizontal. I want the resultant force per unit volume acting over here. Given gamma sat is 20, gamma W is 9.81. So now with this, let's go back. So now you observe somewhere over here, this is element C. This is a small element. Let's take out element over here, please. This is element C, and you know the seepage is going to be horizontal seepage. When it is going to be horizontal seepage, this is the third time we are discussing the same thing. You know that always that submerged weight per unit volume acts downward and seepage force per unit volume acts along the direction of flow, gamma W into I. Then what is the resultant force per unit volume? So first you find out the I value. What is I value? H by L. H 2.8 by 14, which is equals to 0.2, and given gamma sat is 20 kilonewton per meter cube. Given, this is a given details, and gamma W is 9.81 kilonewton per meter cube. So now if you observe, resultant force per unit volume is equals to root of gamma dash square plus gamma W into I square. So root of 20 minus 9.81 whole square plus 9.81 into 0.2 square. So find out this value, then you will be ending with the value as 20 minus 9.81 whole square plus 9.81 into 0.2. So which is going to be 10.38 kilonewton per meter cube. So if you wanted to do decimals, there is nothing in this question. The question is bigger, but the answer you see, how I have applied Darcy. From the Darcy, I got the HB. And you know the horizontal seep is already we discussed all these things. Then we can find out the resultant force per unit volume. No use of clay layer because in this clay did they mention any, see, you observe the question clearly. Once you see the question clearly, they mentioned it clearly, right? There is a hydraulic gradient in pervious layer strata causing horizontal flow. So they gave the details of all the details of the sand only, and you see the laboratory results of the sand. They are not asking you to find out the effective stress. If they ask you the effective stress, then there would be any value. Arey, what is the head loss, Ray? Ray, what is the meaning of I value? What is the meaning of I value? Tell me, please, first of all. What is the meaning of I value? H by L. Yes. What is the meaning of I value? H by L. And what is the total length over here? 14 meters. And what is the total head loss is going to be? What is the total head loss we got? 2.8. Okay, fine. Let's say some of the students, so this I value, this I value is nothing but I is equals to total head loss by total length, sir. I am not asking you the head loss at point C. I am not asking you the head loss at point C. This I means total. And you forget all the basics now. Have you forgot all the basics? What is I value? Hydraulic gradient means total hydraulic head by total seepage length. That does not depend upon the point C. Whether you take here or here or here, this is I value. You see, what is this slope? The slope is going to be constant or not? So now that's about this question. You please go through this question once again. So this is the values that I have mentioned. And now let's see the next question. In the case of ESC, they won't give this question. They will give you the HB value. In the case of ESC, if they ask ESC means IS prelims, they will ask this question only. They cannot ask you this question because there is a roots represented over here. So, and if that is the case, they will mention you gamma W as a 10 value. If they mention gamma W as a 10 value, now you see, if I take gamma W as 10 value, then 20 minus 10, 10 square, 100 plus 10 into 0.2. 10 into 0.2 means 2, right? Yes. So 100 plus 2, 102. Root of 102, root 100 is 10, na? Root of 102 means just 10 point, just 10 point something. That's it. I hope you understood now. So this much logical questions will come means it will be very difficult to solve in exam. This is not at all a logical question, Baba. This is not at all a logical question. When there is a flow, then there is a Darcy Aya, Q Kia, but they have given the velocity. So this is not at all a logical question. This is the basic questions only. You please go through the questions once again. And it's all about yourself. If you are making yourself feeling difficult, then you will feel the same way. So that I am going through each and every point. This is a basic. There's not a logic over here. The resultant force per unit volume is same at every point. Yes, because these are going to be gammas, right? Unit weight is not going to be changed. Unit weight of water is not going to be changed. I is not going to be changed. So in that element, wherever you take, there the resultant force per unit volume is going to be same. Now, and if you want the same answer, you please go through the yesterday's previous gate question. I explained this type of question yesterday there also. So if you want, you can go through that question also. Now, let's see the next question. An upward C-pace. An upward C-pace is shown here. See, this is the type of questions I have given you, and I asked you to solve different models. I gave you n number of models. I am not going to solve this question. I'm not at all going to solve this question. That's up to you. Whether you want to solve it or not, it's up to you, because I have given n number of examples for this one. For a C-pace problems are to determine the effective stresses, total stress, and pore water pressure. How? You will get to know, but you can apply the logic over here directly. I'll tell you the logic instead of going for the basic. I go for the logic directly here. The logic is, you see here. So they mentioned, yes, this is an upward C-pace case. So what they're asking is find out the effective stress and what is the upward C-pace per unit volume. See, what is the meaning of upward C-pace force per unit volume? See, this is a C-pace force per unit volume, which is nothing but gamma W into I. That's it. That is C-pace force per unit volume. Don't think that is a resultant force per unit volume. Now, you see this question, they are asking the effective stress at a point A. See, effective stress at point A. I'm leaving the remaining questions as an assignment problems only, so I'm not going to solve any of the further questions. So if you leave this, means after all discussing this many examples, these many questions, if I solve these questions also, then there is no meaning of me to say the classes. So I'm not going to solve these questions. I'm leaving you. The only questions I'm leaving you is the 7th, 8th. If you cannot solve question number 7 and 8, then it's better you don't attend to my classes. I'm telling you seriously, it's better you don't attend my classes if you are not solving question number 7 and 8. And question number 10, that is similar to the question number 1, 2, and 9. So you have to solve these questions. That's all with this chapter. Question number 10th question. Okay, fine. So as most of the students were asking the question number 10. I'll just explain you. I don't solve this question, question number 10. So I'm not going to solve, but I'll just give. A trench is excavated in fine sand for building up to a depth of 4 meters. I think there is a small correction should be there in this question. I think so, because you see, this is 2.5 meters, right? So this is 3.5 meters. Please, everybody, this small correction. This correction has not done this material. So, but it was done. Means in the classroom I used to do this correction. You please observe this. Everybody, you please observe. It is not a 4 meters. You please correct this one. It is not a 4 meters. That is a 3 meter, 3.5 meters. So they have given the depth of excavation as a 3.5 meters. And verify whether the bottom of the trench is subjected to quick condition. The soil has a GS 2.65 and void ratio 0.7. You see, you know that how to find out the whether bottom of the trench is subject to quicksand condition or not. Find out the factor of safety, IC by I. You know IC is equals to G minus 1 by 1 plus C. You have G and you have a wide ratio. And what is I? H by Z. You observe the C phase is going to be takes place like this only, right? Yes or no? The C phase takes place like this only. Then this is nothing but the Z value, and the difference between the water levels, this is going to be the H value. So H is equals to 2.5 and Z is equals to 2 meters. You please find out that I value 2.5 by Z as 2. You can find it out and you can get it done. So the only change that you need to do here is, please go through this is not 4 meters, this is 3.5 meters. That's what I want to say. Please change it. This is 3.5 meters, not 4 meters. So this is H value difference in the water levels. And this is the upward seepage. This is upward seepage, right? Yes. This is the Z value, upward seepage value. So you please go through this question. And I have explained you all these things. So now that's all from my side. Now let's start a new chapter. So this is the last chapter of the seepage. So now again, this is going to be interesting. So far we have seen one side of the coin. Okay, fine. Sorry, I did not discuss the previous ESC questions of this chapter, right? Let's have a look over that one. Yes. Everybody, please have a look over here. It won't take much time. So you please look over here. I mean, these are ESC questions. These are the previous ESC questions. So it can be taken very less time. Now, assertion. As you know, different type of questions that can be seen. In the case of this type of questions, you observe. So assertion, quicksand is not a type of sand, but it is a type of condition arising in the sand mass. Yes, I told you quicksand is not a type of sand, it is a condition. Assertion is true. When the upward seepage pressure becomes equals to the pressure due to submerged weight, which means upward seepage pressure means gamma W into H, submerged weight means gamma dash into Z, then effective pressure becomes 0. Yes. So quicksand condition occurs when upward seepage pressure becomes equals to the submerged pressure, and that is going to be happens in the case of the sands, because sand is a corrosionless soil. So assertion is true, and in order to cause the quicksand condition, then the effective stress, see, yes, quicksand is not a type of a sand, but it's a type of condition arising in a sand mass. And when it is going to be occur, when the upward seepage pressure becomes equals to pressure due to submerged weight, then the effective pressure becomes 0. So both A and R, assertion and reason, are true, and R is a correct explanation of A. So the answer is going to be A. Now let's see the next question. In this question, see this type of question we have seen in the case of the gate also. So now an upward hydraulic gradient I of a certain magnitude will initiate the phenomena of boiling in granular soils. The magnitude of the gradient. Hey Baba, what is the magnitude when quicksand condition occurs? Quicksand occurs when I is equals to IC. And what is the IC value? I told you IC value is equals to almost equals to 1. You please go through the notes. I have mentioned you. Generally, the critical hydraulic gradient is going to be 1. So answer is C. Now, you see this question. Yes. Which one of the following equation gives correctly the relationship between the specific gravity G and hydraulic gradient I to initiate a quick condition with a void ratio as 0.5. They have given E void ratio of 0.5. So whatever the IC relation is equals to G minus 1 by 1 plus E, then G minus 1 is equals to I value as a I into, see they have given as a void ratio which is going to be 0.5. So 1.5 I. Then G is equals to 1.5 IC plus 1. So answer is going to be answer C. Now, yes. You see this question, a sand deposit has a porosity. A sand deposit has a porosity which is going to be N value. What is the porosity? 0.375 and specific gravity 2.6. What is the critical hydraulic gradient? So G minus 1 into 1 minus N. 2.6 minus 1 into 1 minus 0.375. 2.6 means 1.6 into 1 minus 0.375, which is going to be 0.625. You see the answers. First of all, you observe the answers over here. You observe, say option A. See, I don't have any calculator, right? I don't have any calculator. As I don't have any calculator, so for this one, how to find out the answer? This is not true. This is not true because the IC value is going to be 1.6 into 0.625, which means obviously the value is less than 1.6. So eliminate A and B. Some of the students were asking, sir, if the question is given in IES without calculator, how to solve, sir? Now you see, sir. See, in the case of IES, you have to go for the elimination procedure. So once we get the final steps, now eliminate the options. Now the options are 1 and 0.75. So now how to, sir? So let's take, sir, what is 1.6 into half, sir? What is a 1.6 into half? What is half? 0.5. Array 1.6 into half itself is 0.8. And 1.6 is into more than half means more than 0.8 or not? Eliminate this. What is the answer? 1. If you solve, the answer is going to be 1. See, I did not use any calculator. Just simply I am eliminating the options and then I am using. So finally, what is the answer I am going to get? Answer is C. So now, next question. Yes, a soil mass under seepace, a soil mass under seepace which has a downward flow. See, this is a downward seepace, Nana. It's not an upward seepace. This is a downward seepace. Please keep that in your mind. Video. I'm not getting video. So now you see here. Yes. So in the case of the downward seepage, which one of the following statements are correct with regard to stresses at any point in the soil? At any point in the soil, effective stress is decreased by an amount equals to seepage force. Is it? You know that in the case of the downward seepage, you know that the downward pressure gamma dash into Z and seepage is also going to be gamma W into H. So is it going to be increases or decreases? Increases. So you see effective stress is normally gamma dash into Z, and due to downward seepage, the pressure has been increased due to the seepage force. So the A is not going to be correct. So now with this, I'll eliminate some of the options you observe here. If you observe, the first one should be eliminated. The first one should be eliminated. So if you eliminate first one, then option A and C are going to be eliminated. Now, when option A and C are eliminated, you see B and D, the common answers are going to be 2. So effective stress is increased by an amount equal to C phase force. Yes. So due to in the downward C phase, effective stress increases. Total stress will change and total stress will be unaltered. You know that I have mentioned you in the case of the no C phase, upward C phase, downward C phase, no change in unit weight. So change in total stress is going to be 0. There is no change in total stress. So delta sigma is equals to 0. If you want, you please go through the notes. In the starting of this chapter, I mentioned you all these points. So 2 and 3 are going to be correct. Now you eliminate this one. I don't need to go for the option 4. So what is the answer? Answer B. Now, you see this question, last question, statement, see for this question, we require the liquefaction. We'll be discussing this question in a shear strain topic. So these are some of the previous grade questions. And if you observe the grade questions, mostly they are focusing on whom? Hydraulic gradient, factor of safety, and this quicksand type. So in this chapter, most of the questions will be occurred if numericals comes in the case of ESC, factor of safety, and critical hydraulic gradient. This chapter is more important for numerical in the case of the gate and the theoretical part in IES. Okay. Here, sorry, I said yes. First thing is effective stress is increased by an amount equals to C phase force, and total stress will change. No, it's not going to be changed, right? The answer is going to be total stress will be unaltered. So answers are 2 and 4. I'm sorry, the answer is D. But while I am writing, I wrote it here as I wrote it here. So no change in total stress. Delta sigma is equals to 0. And due to downward C phase, gamma dash into Z, gamma W into H. So effective stress is going to be gamma dash into Z plus gamma W into H. So effective stress increases and no change in the total stress. I'm sorry for that. Now, so with this now stop your questions and start understanding the things. Now chapter number 9, C phase analysis. Chapter number 9, C phase analysis. See, so far up to now, whatever the discussion we made from the chapter number 6 onwards, you please observe what I am going to see. This point is very, very important. What is the difference between the previous chapter 6, 7, 8, 9 and this means 6, 7, 8 and this chapter. See, from from 6, 7, 8 chapters, what we learned is QKIA, how to determine the discharge. First of all, we learned about the hydraulic gradient. I is equals to H by L, total hydraulic head by total C phase length, and how to find out the head loss at any section, I into length up to X. This is the head loss at any section. And then we discussed about how to determine the pressure head at any section. Pressure head at any section is a total height from the top minus Hx, means the total height of the piezometer minus Hx. And then we discussed about Q is equals to KIA And then we discussed about effective stress is equals to total stress minus pore water pressure. And whereas pore water pressure is depends upon gamma W into HP, means the pressure head at X. So, and then we discussed about factor of safety. What is the factor of safety? IC by I. So these were the things that we have been discussed so far. If you confined everything, then these are the things only. I did not go for much equations, did I? I did not go for the much equations over here. So, and yet a critical condition, you know, yet simply, I know I'll remember this one as yet a critical condition, effective stress is equals to 0. So these were the things that we learned in the previous chapter. But now, my point is, observe clearly what I am going to say. This factor of safety depends upon whom? I. Because IC is going to be constant. This is a constant value, right? So this factor of safety depends upon whom? I. And pore water pressure, effective stress depends upon pore water pressure. Pore water pressure depends upon pressure head. And this pressure head depends upon head loss. And this head loss depends upon I. Eventually, this entire thing is going to be depends upon whom? I. And now you come to the discharge. The discharge depends upon whom? I. So, discharge depends upon hydraulic gradient. Factor of safety depends upon the hydraulic gradient. Pore water pressure depends upon the hydraulic gradient, because the pore water pressure depends upon pressure head on the head loss, and head loss depends upon the hydraulic gradient. Which means all of these things, the common factor is a hydraulic gradient. And what is a hydraulic gradient? H by L. And how to determine this H? Difference between water levels. And now, what is L? What is L means? A seepage length. So far and so good. I told you, whenever there is a seepage, along the length of the seepage, there is a length known as seepage length. But my question, in reality, beneath the dam, do you know exactly what is the length of seepage? Do you know exactly what is the length of seepage? We don't know. In the reality, beneath the dam, throughout the soil, there is a seepage. And you cannot predict the exact seepage length. When there is no seepage length, then you cannot find out the I value. See, these are all our approximate analysis. Yes or no? Yes or no? Because whatever the soil mechanics I told you, this is made of simplifying assumptions. So if I know the length, then I can find out I. Now my question for you is, I don't give any seepage length. I don't give you any I. But still, I want this head loss at any section and pressure head at any section, discharge, effective stress, factor of safety, and all these things, but without knowing the seepage length. So far and so good, I explained you with the seepage length. Now I am going to find out the seepages, pressures, factor of safeties, head losses, everything without using I value or without using seepage length. That's what we are going to see in the seepage analysis. So now let's start our session. Again, chapter 9, seepage analysis. So now, in the case of the seepage analysis, at first, so what we are going to learn here is, for any engineering solution, for any engineering problem, it requires a mathematical solution. So for any engineering related problem, it requires mathematical solution. So what is this mathematical solution over here? The mathematical solution over here is, so we are going to use a Laplace equation for flow related problems. For flow problems, Laplace equation for the flow problems. So now, what is this Laplace equation? I hope you may heard about this Laplace equation. So the people who have completed their fluid mechanics, they might have heard about this one. So now let's recall our dam. Let's recall our dam. Whatever the dam we know. So if we take, this is the dam. And this is the water levels. And you see, this is a dam, and beneath this dam, the flow is going to be happen. So now, this is a soil, and I am going to discuss about the flow related problem in the soil mass. For that, I am going to use the Laplace equation. Sir, what is this Laplace equation, sir? See, if this is a flow over here, if this is a flow over here, when the flow is going to be happen, now you see, if I take an element over here, a soil element over here, if I take a soil element over here, let's take the soil element aside. This is a soil element. In this soil element, there is a velocity in the x direction. There is a velocity in the y direction, Vy. Because you know, in the x direction, Vx, in the y direction, it is going to be Vy. So whether it is upward or downward, you know that there is a velocity of the flow, which is going to be Vx and Vy. So now, if you observe clearly, the Laplace equation says as, what is the Laplace equation, sir? I'm not going to derive the Laplace equation. I'm using the Laplace equation. So forget about the derivation of the Laplace equation. So now you please focus on the Laplace equation. So what is the Laplace equation is? It's a variation of the flow parameter. Variation of the flow parameter. See, let's take this length as dou x. And let's take this length as dou y. Elemental length as dou x and dou y. So whatever the variation of the flow parameters in x and y directions, summation should be 0, which means the variation of the flow parameter Vx, dou Vx along the direction, which direction? Dou x, less the variation of the flow velocity dou Vy along the direction with respect to dou y is equals to 0. Simply, the variation of the flow velocities in all the directions, summation is going to be 0. X direction Vx, y direction Vy, and if it is a 3-dimension, then z, dou Vz by dou z. So this is the Laplace equation. Now let's see how this Laplace equation is going to be. So how this Laplace equation is not going to be, is going to be useful for this. So now this Laplace equation, in the case of the soils, according to Darcy, from Darcy, you know that V is equals to Ki. Yes, for this element, V is equals to this soil mass must be having some quotient of permeability K into elemental. Nana, I means H by L, where the L, if it is a horizontal length, the length is horizontal. If it is a vertical, vertical. So as I am taking a small element, there is a horizontal shape as dou x, vertical shape as dou y. So I can write this one as a dou h by dou s. What is meant by dou h by dou s, sir? Dou h, small elemental head, dou h by small elemental length, dou s. Now you see, as there are, see, generally the soil exists as a isotropic or anisotropic. You know that. You know that generally the soil must exist as a anisotropic, which means if the flow velocity is going to be Vx, then what is the permeability? Kx. I hope you remember the Kx. What is the meaning of Kx? The average permeability when flow is parallel to the bedding plane. So dou h by, what is dou s here? What is s over here? Length. S means length over here. Space, Nana. S means space. Now I can write as dou x. Then what is Vy? Ky into dou h by dou y. Dou h by dou y. But we assume in Laplace equation, soil is assumed as homogeneous and isotropic. Flow is steady. What is the meaning of steady here is discharge is constant. Flow rate remain same, means no change in the flow rate. So now if I substitute in this equation at first you see in the case of the Vx, if you substitute over here, if you Vx, see the Kx is going to be constant, then dou by dou x of dou h by dou x, dou by dou x of dou h by dou x. So now let's take this as the equation 1. Substituting in equation 1, then Vx, Kx is going to be constant, Kx into dou by dou x of dou h by dou x, which means dou square h by dou x square plus Ky into dou square h by dou y square is equals to 0. This is for the anisotropic soils. Mind it, this is for the anisotropic soils. But for isotropic, Kx and Ky both are same. You know the meaning of isotropic. I don't need to say the homogeneous and isotropic again, because the meaning of isotropic is wherever you take in the soil mass at a particular point in any direction, horizontal and vertical, the properties should remain same. So then the equation is going to be finally convert to dou square h by dou x square plus dou square h by dou y square is equals to 0. There was one previous gate question also. Which one of the following equation represents the Laplace equation when a flow is passing through soil? Dou square h by dou x square plus dou square h by dou y square. And if it is an anisotropic soil, then this is going to be the equation. See, this is anisotropic soil, Nana. This is anisotropic soil, and this is going to be the isotropic soil mass. So finally, yes, this is the Laplace equation. From this equation to this equation, we have made a one. This is a family of curves which are orthogonal to each other. Sir, what is the mean by orthogonal, sir? Orthogonal means perpendicular to each other. What is that? Perpendicular to each other. So you see dou square h by dou x square, x direction, and dou square h by dou y square, y direction. This dou square means this is a parabolic variation. That's the reason why I call it as a curve. It is a family of curve which are orthogonal to each other, and one of that curve is going to be flow lines. This is the flow lines, and the other one is going to be equipotential lines. I hope you might have heard about this one, flow line, or we can write it as a streamline also, and this one is equipotential line. So in the case of this entire equation, this equation consists of a family of curves which are orthogonal to each other, and one is the flow lines, other one is the equipotential lines. So with this, what I want to say in this slide is, we are going to discuss about a Laplace equation which consists of two curves. One is a flow line, other one is a equipotential line. Sir, you are saying line and you are saying curve also. Baba, for the namesake I say line, but when I draw it as a curve. So I hope you understood what we are going to discuss here is flow lines and equipotential lines. So now let's see what is this flow lines and what is the equipotential lines. Yes, soil is incompressible. Solids are incompressible. That's there. That is common assumption. So apart from that, soil is incompressible. In soil, solids are incompressible. That's one of assumption only. So we don't need to worry about those assumptions. Okay. So now, let's see the definitions. Flow lines are stream lines. Flow lines are stream lines. So what is this of flow lines, sir? See, the name itself says everything over here. Please understand what is meant by flow. Flow line. Flow line means the line that drawn along the direction of flow. If the flow is horizontal, along the horizontal direction, if I draw a line, that is a flow line. See, just simply what I am showing you, this is nothing but a flow line or not. You observe here. What is this? This is nothing but a flow line, because this is a line that I am drawing along the direction of flow. So if I join all these points, then that is a line known as flow line. So flow line means a line that is drawn along direction of flow, which is known as flow lines. Now second one is equipotential line. So what is equipotential lines? The name itself says, see, you split equipotential lines. The line along which, potential means here total head, Nana. Potential means total head. The line along which total head remain, equi means same. Equipotential line. So I can say the lines along which total head remain same. The line along which total head remains same. That is going to be equipotential lines. And see, these equipotential lines, see, one is going to be a flow line, other is going to be equipotential line. Now, if you observe, these are going to be orthogonal to each other or not, because one is X, other one is going to be Y. And the combination of these two, we are going to call it as flow net. Flow net. So what is a flow net, sir? flow net is a combination of flow lines and equipotential lines. So now flow net, it's a network or combination of flow lines and equipotential lines. See, I can call this flow line as a streamlines also, so we don't need to worry about that. Equipotential lines. Okay. These are the definitions over here. So now you can see the node point over here is node, flow lines and equipotential lines are orthogonal or perpendicular to each other. See, the symbol is a perpendicular symbol, it's not a parallel symbol. Orthogonal or perpendicular to each other. So now let's see how this a flow line or flow net. You see finally what is this flow net? Flow net means network or a combination of flow lines and equipotential lines. Now our point is how this flow net is going to be helpful for us to determine discharge, to determine head losses, to determine the pressures, to determine the factor of safety, which means whatever the things we learned in the previous chapter, how we are going to find out by using the flow net. So for that, first we need to look over what are the characteristics of the flow net. Characteristics of a flow net. So what are these characteristics? So for that, now let's see. Please listen. This is very, very important. It's nothing new, but you know it very well. You observe. Let's take this is an orbit. This is a higher water level, and you see. Let's take this is a lower water level. Let's say higher water level, and this is a lower water level. And now let us take an arbitrary datum also. Let us take an arbitrary datum. Okay. So now, if you see, this is an arbitrary datum I have taken. So let's take this as a datum. Now, if you observe, this is a water level and this is a water level. And you know that flow takes place from higher energy level to lower energy level. Flow takes place from higher energy level to lower energy level. Arbitrary means reference, Nana, not constant. Arbitrary means reference datum. So now you listen carefully. So you see, first of all, let's see the flow lines. So now I am erasing this figure also because I have shown you the flow will take place from the higher energy level to lower energy level. Yes or no? Yes. So let me represent that. What might happen? So let me represent that also. That water level would be there. So flow takes place from higher water level to lower water level. Now, whenever there is a flow, along the direction of flow, if I draw a line, the line that drawn along the direction of flow is nothing but a flow line. So now let's draw a line along the direction of flow. So along the direction of flow, if I draw a line, this is going to be a line. Sir, you said line, but you are drawing curve. Sir, I say the line, but you know the equation. What is the equation? Dou square h by dou x square plus dou square h by dou y square. So now you see one of these family of curves represents the flow lines, other one represents the equipotential lines. Whatever the flow, whatever the line that drawn along the direction of flow, here is flow line. So what is this line now? This is going to be a flow line. And likewise, you're going to see this is the flow, right? Likewise, you're going to see n number of flow lines. You're going to observe n number of the flow lines. So first of all, what are these? These are nothing but flow lines. Let's see the characteristic of the flow lines first, and then we go for the equipotential lines. Okay. So you see, when there is a flow, then definitely there is some discharge passing through the flow, means a flow rate as a Q. Now, if you observe, all these are flow lines or not? Yes. And in between these flow lines, there is a space. You see this space. Whatever the space present between the flow lines, see, this is a flow line, this is a flow line, this is a flow line. So when the flow is going to be takes place, some flow passes through this space, some flow passes through this space. So now whatever the space present between the flow lines over here, that space is known as flow space or flow channel. That space is known as flow space or flow channel. So now you see, if you observe over here, so whatever this space I am going to represent it as this space, I'll be represented as flow space or flow channel. So what is this flow space or flow channel? Now, characteristic number 1. Between any two flow lines, a space between any flow lines, any two flow lines, there is a space known as flow space or flow channel. Flow space or flow channel. Okay. So now what happens over here, sir? So then, okay, sir, fine. But why do we need to worry about this flow space or flow channel, sir? So now you see, sir, each and every flow space has some discharges, sir. Let's say the discharge passing through this flow space. Let's say the discharge passing through this flow space. Whatever is going to be the flow space. So I mentioned you this as a flow space over here. And now, whatever the discharge passing through this flow space, let's take it as a delta Q1, and let's take it as a delta Q2, and let's take it as delta Q3, and so on. See, through each and every flow space, there is some discharge. Now, the characteristic of the flow net is, it was mentioned for this flow net, the characteristic. These characteristics means what is the behavior of the flow net. So now the characteristic of the flow net means, see, some of the students are in reality there is no space. Na, Baba, please, thoda dimag idhar rakho ra bhai. These are about our assumptions, Nana. In reality, you cannot see all these things. In reality, we cannot analyze. If you do analyze, then you go for an analyze, right? That's what I'm saying. In reality, we cannot see that, but we need something to analyze. This is a mathematical technique. So now, between any two flow lines, there is a space, and you see whatever the flow channels are there, between any two flow channels, the flow or the flow rate is going to be same, which means delta Q1 is equals to delta Q2 is equals to delta Q3. Now the point number 2 is, between any two successive flow channels, flow rate passing through any two successive flow channels are seen. Any two successive flow channels are seen. So which means you take a flow channel number 1, what is the flow rate? Delta Q1. You take the flow channel number 2, what is the flow rate? Delta Q2. You take the flow channel number 3, what is the flow rate? Delta Q3. And you know that total discharge Q is equals to delta Q1 plus delta Q2 plus so on. I hope you understood the meaning over here. So you know the total discharge means delta Q1 plus delta Q2 plus delta Q3 and so on, and each discharge value is going to be same. Now can I represent this delta Q1? See how many discharges are there here? 2. Delta Q1 plus delta Q2. And you know delta Q1 and delta Q2 both are going to be same. So now I'll represent everything as a delta Q. So now as a 2 are going to be same, can I write Q1 plus Q2 as a 2 times of delta Q? Yes. When there are two flow channels, then 2 rates, 2 into delta Q. For example, if there are 3 flow channels, delta Q1 plus delta Q2 plus delta Q3, all are same. Can I write all these things as a delta Q, which means 3 times of delta Q. 4 flow channels, 4 delta Q. 10 flow channels, 10 delta Q. N flow channels, NF delta Q, where Q is equals to NF into delta Q. This is the first and foremost characteristic in the case of flow lines. This is the first characteristics. So now what is this NF, sir? Where NF is number of flow channels. Sir, how to find out the number of flow channels, sir? Sir, you see, sir, how many number of flow lines are there? 1, 2, 3. 3 flow lines are there. And you know that between any 2 flow lines, there is a space known as a flow space. Array, here there are 3 flow lines, right? 1, 2, 3. Then how many flow channels are there? 2. So 3 flow lines, then the number of flow spaces are going to be 2. Then if I say 10 flow lines, then number of flow channels are going to be 9. So can I say this number of flow channels can be find out as a number of flow lines minus 1. How to determine the number of flow channels? Number of flow lines minus 1. So in examination, either they will mention you number of flow lines or number of flow channels. This NF means not line. That NF means channel. Number of flow, NF, number of flow channels, which is going to be number of flow lines minus 1. So each flow channel has a discharge, and each and every discharge is going to be seen. So this is the characteristic number 1 for the flow channels. Now let's see the equipotential line. Let's see the equipotential line. So now coming to the equipotential line. What is the equipotential line? You know that equipotential line means the lines along which total head remains same. And these equipotential lines are going to be orthogonal to the flow lines or not. Now what I ask you is simply you draw a line perpendicular to the flow lines. You see this is a flow curve, yes. And for this flow, see if this is a flow, then what should be the perpendicular? The perpendicular is going to be this one. So now you draw a line exactly perpendicular to the flow line. So now here is a one equipotential line. Similarly, here is one more equipotential line. This is one more equipotential line. So let me draw it down in another fashion. One equipotential line, one more equipotential line, and one more equipotential line. So now you tell me what are these lines? These lines are equipotential lines. So the equipotential lines means the line along which a total head remains same. See, on this line, the total head is going to be same, Nana. No matter what, on this line, the total head is going to be same. So this is a line where the total head is going to be remain same. At this, all the points, the total head is same. What is total head? Pressure head plus datum head. So now you see what is the characteristic of a flow equipotential line. After this one, I'll give a break. So please wait for that. Now you observe. Let's take these are the 3 points. 1, 2, 3, and you see there is a space where these flow lines and equipotential lines are going to be intersected. Yes or no? See, these are the 2 flow lines and these are the 2 equipotential lines. So the space intersected by the 2 flow lines and 2 equipotential lines are known as flow field. This is known as flow field. So let's take the flow field outside. Now you see whatever, this is nothing but a flow field, right? Yes, this is a flow field, and you see this is one flow channel or not. Through this one flow channel, how much discharge is going to be passes? Delta Q, because you see this is one flow channel and each and every channel flow rate is going to be same. So now let's take the flow field dimensions are delta B, this value, and delta L, the length of the flow field as a delta L, and is going to be delta B. See, this is a flow field which is intersected between 2 flow lines. This is the flow line, and here this is a equipotential line. So whatever the space intersected between 2 flow lines and equipotential lines are going to be the flow field, and the element of flow field element has a width of delta B and a length of delta L. So now what is the characteristic over here is whatever the number of flow fields are there, so whether the flow field may be smaller flow field or larger flow field, means, see, don't think all the flow fields size is going to be same. It will be varies, but the point over here is ratio of dimensions of any flow field should be same, which means what is the ratio of flow field? What is the ratio over here? Delta B ratio, delta B by delta L is constant. So for any flow field you take, the property is you take any flow field, its ratio of dimensions should be constant. So now by using this one, let's go to the equipotential line. In the case of the equipotential line, at first let's insert our piezometers over here. This is point number 1 and this is point number 2. See, I am taking on the equipotential lines, mind it. See, this is one more piezometer. So now these are the piezometers that I have been kept, And you see, this is the initial water level, right? And this is the final water level. This is initial water level and this is the final water level. So the total difference between these two water levels is going to be the total head loss as a H. Now you see, when there is a flow, there is a head loss or not. You know it, you know the concepts, just simply apply again. So when there is a flow, there is a head loss. Initially, if the flow is going to be starts like this, now let's say initially this is the water table or rises up to this point, okay? Because let's say this is the starting point and initial piezometer water level raised to the corresponding water table. Now you see from here to here, how much distance we are going to travel? Delta L. When you travel a length of delta L, then definitely the water level in the piezometer will fall or remain same. The water level in the piezometer will definitely fall. So whatever this fall on an elemental fall, let's take it as delta H1, which means that is going to be head loss over a length of one flow field. What is this flow? What is this, Nana? This is going to be a flow field or not? So in the case of this flow field, now you tell me, when the flow is taking place from one equipotential line to other equipotential line, a length of delta L is going to be traveled, and from one to other equipotential line, the water level falls by delta H1. Similarly, now come to this point, if I insert a piezometer over here, here also the water level will fall. So now whatever the water level falls further, let's take it as delta H2, because from here delta H2. Now if I go further and further and further, then there is a head drop, a drop. You see delta H1 plus delta H2 plus delta H3 plus delta H4 and so on is equals to total head loss. Yes or no? So now can I say between any two equipotential lines, there is a loss known as a head drop, where this delta H is going to be head drop. This delta H is going to be head drop. So now what is the characteristic of the equipotential line, sir? Now you observe here, sir, between any two successive equipotential lines, see, this is a one equipotential line. What is the drop? Delta H1. And this is other equipotential line. What is the drop? Delta H2. Between any two successive equipotential line, the head drop remains same. The head drop remain same. So this is the other characteristic. Between any two successive equipotential lines, head drop always same, which means delta H is equals to delta H1 is equals to delta H2 is equals to so on. Delta H2 is equals to so on. So now, what is the total head loss? The total head loss means delta H1 plus delta H2 plus so on. You see this one, what is the total head loss over here? The total head loss is equals to delta H1 plus delta H2 plus so on. Now, as I told you, there every drop is going to be same. Then, for suppose, how many drops are there here? How many drops are there here? 2 drops. And both the drops are same or not? Then what is the total head loss? Delta H1 plus delta H2. As both are same, then I can write as a 2 into delta H. For example, if there are 3 drops over here, 3 into delta H, n drops, then nd into delta H. So which means here H is equals to nd into delta H. So this is the next characteristic. What is this nd, sir? Here the nd is number of equipotential drops. Number of equipotential drops. Sir, how I got these drops over here, sir? You please see between any two equipotential lines, how many drops are there? One. See here, how many drops are there? Two drops are there. Two drops means how many equipotential lines are there? 1, 2, 3. So 3 equipotential lines are there, which means 2 drops. If there are 10 equipotential lines, then how many number of drops? 10 minus 1, which is going to be 9 drops. 20 equipotential lines, 20 minus 1, 19 drops. So just like the number of flow channels is equals to flow lines minus 1, similarly number of drops is equals to number of equipotential lines minus 1. So these are the two characteristics, and with these two characteristics only we are going to discuss the applications. So what is the first characteristic? Q is equals to NF into delta Q, and next characteristic is going to be Q is equals to H into H is equals to ND into delta H, where ND is the number of drops and delta H is as each drop, means a single drop. So between one equipotential line to other equipotential line there is a drop, and that drop is delta H, which is equal to be total head loss is equals to ND into delta H. So now the other characteristic is flow net once drawn will not change for a, or I'll say this point later. Okay. So now whatever the applications are there, you please tell me. So now applications of the flow net. So what we need to find out here is, once we know the characteristics of the flow net, then what are the application of the flow net? See, there are some other characteristics. I'll say those characteristics while I was deriving the applications. So you please see this. I'll write down the applications and we'll see the discussion after the break. So, but for that, you see, what are the applications of the flow net are? Number 1, seepage loss or flow rate. So what is the seepage flow rate of discharge in terms of meter cube per second per meter? You know that, you see, go back over here. You know that whenever there is a flow, then definitely some flow rate is going to be passing through the soil mass or not. So what is the seepage flow rate? Earlier we have find it as by means of Q Kia. Now let's see what is the equation. And second one is seepage pressure. You know that seepage pressure is a PS. And third one is uplift or pore water pressure, represented with a U. And fourth one is exit gradient, represented with a I exit. So I'll tell you all these things are. See, when there is a seepage, you know that initially you start with the difference. What is this difference between this H? You know that initially the head starts with the hydraulic head of H. And while moving, so this is going to be less than H or not. Let's take this as a 0.6 H. So how to find out this seepage head? Here and here, but finally it reaches over here 0. So once you know the seepage head, how to find out the seepage pressure and how to find out the pore water pressure, how to find out the exit gradient, all these things we'll see after the break. So now it's 11:20, about to 11:20. We'll have a break and we'll be starting our session at 11:40. 11:40. So you please be in the means. You see, just from your timings, you take 20 minutes break. Now it's about 11:20. So I'm giving a 20 minutes of break time. Please have a break, and please come back, and after the break we'll be seeing these applications of the Flownet. Okay. So now, so everybody back. Okay. So now you see, these are the applications of the FlowNet. Now let's see by using these characteristics of the FlowNet, how we are going to find out the applications of FlowNet. So for that, let's take again. Dam. So this is a dam where you see upstream and downstream bed level. These are going to be upstream and downstream water levels. And this is the difference between the water levels. And let's say somewhere below, this is the datum. Means this is a hard strata. This is not a datum. This is a hard strata. Hard strata. So now you observe over here, if you see the difference between water levels as H, this is upstream water level, and here this is going to be downstream water level, and this is a dam, and this is upstream bed level, and this is downstream bed level. Now you see the seepage will be taking place between this below the bed level, this is the ground level, and above the hard strata, because this is the soil mass where the seepage is going to be taking place. Now what I have to do is, in this soil mass, when there is a seepage, I need to find out this seepage loss rate and seepage pressure, uplift pressure, exit gradient by the usage of the characteristics of the FlowNet. So for that, the first thing that we need to know here is, so how to draw the FlowNet. How to draw the FlowNet. So for drawing this FlowNet, you must need to know one thing. So if you observe here, I have shown you the flow along the direction of flow, whatever the flow is going to be, whatever the line is going to be flow line, and perpendicular to that, that is going to be equipotential line. So for that means in order to introduce you much more, some more complexity, what I do is I will attach a sheet pile wall on the upstream side or downstream side. It's up to you. I'm just making sure. This one. So I'm giving you a sheet pile wall over here. This is a sheet pile wall. I don't need to say that what is it sheet, is it a sheet pile wall or not. Now let's go with the figures. How the flow is going to be starts along the direction of flow. Now you see everyone, you know that flow is going to be starts at this point and ends at this point. Now the flow starts downward here and flow ends upward over here. So in between, along the direction of flow, if I draw a line, that line is nothing but flow line, because the line that drawn along the direction of flow. So now what I do is I just simply draw a line. I just simply draw a line along the direction of flow. You observe here. Along the direction of flow. You see this line, can I say it as so I can say this one as a flow line. So whatever the line that I have drawn along the direction of flow over here, this is nothing but a one flow line. So this is known as flow line. Okay. And now along the direction of flow, likewise, n number of flow lines can be drawn or not. Similarly, this is one more flow line. This is one more flow line, and again this is one more flow line. See what I have drawn over here is everything is a flow line. Please keep that in your mind. All these things are flow lines. So, sir, how I have to draw these flow lines in reality, sir? Sir, this is a graphical procedure. What you have to do is, first of all, you take a scale. In reality, whatever the field dimensions are there, you take some scale. There is some fixed scales would be there. So then based upon that only you have to go for the drawing of the flow net. But forget about the graphical procedure. You look over the concept. You look over the concept. Forget about the graphical procedure. So in examination, they are not going to be asked to draw the flow net, but you have to understand what is this flow net. Yes. So now theoretical procedure I am saying, not a graphical procedure. So whatever, this is nothing but the flow lines. Can you please tell me how many number of flow channels are there here? How many number of flow channels are there here? So I'll see the comment sections now. How many number of flow channels are there? Okay. Okay. Okay, fine. See, I got answers. Now you see. Let's stop. Okay, I have got the some of answers from your side. And it is mentioning that some of the people are saying 2, some of the people are 3, some of the people are 4. See, according to the flow lines that I have drawn, between any 2 flow lines, there is a flow channel. So there are 2 flow channels. But if you see carefully, see, don't you think the flow will pass like this? Yes. The flow will pass here. Yes. The flow will pass here. Yes. And the flow will pass over here also, which means, you see, I have drawn 3 flow lines. But if you observe along the base length, means along the base length, don't you think this entire water will travel along the base length of the dam? Don't you think the entire water will travel to the base? And don't you think the water will travel here? Don't you think water travel over here? Yes. Don't you think water travel over here? Yes. See, here, the point I want to mention here is, see, not only the flow lines that I have drawn, but also the boundaries of the dam, the base width of the dam and the harder rock, both are going to be behaves like a 2 more flow lines. What is meant by flow channel? The space where the flow is going to be passed. Here there is a flow, 1 flow channel. So I'm going to take it as a 1. And here there is a flow, 1 more flow channel, 2. And here there is a flow, 1 more flow channel. This is 2. Here there is a flow, the 1 more flow channel, 3. And here there is a flow, 1 more flow channel, 4. So there are 4 flow channels, not 2 or 3. You can ask me, sir, you have drawn 3 flow lines, then which means 3 minus 1, the flow channels are going to be 2. Yes, but you observe the base length of the dam. See, this is going to be the base, right? Whatever the base, this base and this hard strata also acts like a 2 default flow lines. So here the point is, boundaries are base of dam and hard strata acts as 2 default flow lines. Then what is the number of flow channels over here? Number of flow channels are going to be, see, 3 I have drawn, 2 are default, so 5 flow channels are there, sorry, 5 flow lines are there, which means 4 flow channels, which means NF is equals to 4 in this 1, 2, 3, 4. So now I hope you understood the flow channel concept over here. Yes, in practical you have to take that. Practically you have to take you have to consider the base of the dam and hard strata into the consideration. You have to take it as a 2 default flow lines. So if you take 2 default flow lines, I have drawn 3 and these are 2. So total 5 flow lines. Then what is the formula of flow channel? 5 minus 1, which is going to be 4. So now let's see. What is the equipotential line? What is the equipotential line? You see, you observe carefully. I told you the equipotential lines. What is the definition of equipotential line? The line along which total height remains same. And in the case of the equipotential line, these lines are going to be orthogonal to the flow lines or not. As they are orthogonal to the flow lines, now you see, so you have to draw this one. You observe carefully. This is vertical, and this is also vertical. Here vertical, here also it is going to be vertical. So now, if the flow is going to be vertical, then flow line is vertical. Then what about equipotential line? Orthogonal means this is going to be the equipotential line or not, which means whatever this line, the upstream bed level and downstream bed level, both are going to be actually like 2 equipotential lines, because this is perpendicular to this value. This is perpendicular here. This is perpendicular here. So I can say the upstream bed level and downstream bed level are going to be behaves like a 2 default equipotential lines. Upstream and downstream. This is about gravity dam, Nana, because I'll be discussing the earth dam also here. And downstream bed level acts as default equipotential lines. Default equipotential lines. Now you see how I am going to draw the remaining equipotential lines. So I will draw the equipotential lines in such a way it should be almost orthogonal to the flow lines. So now you see, there is a one equipotential line. There is one equipotential line. This is going to be almost perpendicular over here. There is one equipotential line. Now you see, what is this equipotential line over here? See, the flow line is horizontal. The flow line is horizontal. Here the flow line is horizontal. Then the equipotential line is vertical. Here the flow line is vertical. The equipotential line is horizontal. Similarly, Now you observe here. So these are going to be the equipotential lines. So you don't need to worry, sir, how many number of equipotential lines I have to draw and all those things. You don't need to worry about that. In examination, they are going to be give you the number of flow channels, or they will give you the figure. So you have to fix how many number of flow channels and the equipotential lines are there. That's it. So if you are able to fix it, then you can find out the answers. So now, wherever there is a flow line, I have drawn the equipotential lines almost orthogonal. You see here perpendicular for this point. This is perpendicular, and you see here flow line is horizontal and equipotential line is perpendicular. So this is how you have to draw the equipotential line. Now, how many number of drops are there? You see, I told you the total number of drops are going to be total number of equipotential lines. Total number of equipotential lines minus 1. How many I have drawn? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 I have drawn, but by default, upstream and downstream bed levels are going to be 2. So 9 plus 2, total how many equipotential lines are there? 11. 11 means how many number of drops should be there? 10. Now let's see. Let's see how to give the numbering for that. You please have a look over here. You know that between any two successive equipotential lines, there is a one head drop. So this is one drop. This is one drop. And this is two drop. This is a one flow field or not? In simple words, how many number of flow fields are there? That many number of drops are there. Because you go back. What is this? This is one flow field. And what is drop? 1. This is how many flow field? 2. 2 flow fields means 2 drops. So how many number of flow fields are there? That many number of drops are there. You please give a numbering over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total how many number of drops are there? 10 drops are there. You can go this one also. You can go this one also. There is going to be 10 only. When there are 10 drops, how many number of equipotential lines should be? For 10 drops, line should be 11. But how many I have drawn? 1, 2, 3, 4, 5, 6, 7, 8, 9. The remaining 2 are going to be default. So here, number of drops are going to be 10. So this is one example I have taken. Now, our first application. Yes. Sir, is it practically possible to analyze our flow lines and flow channels? Practically, if it is possible, then why we are drawing this one? This is a graphical. What is the meaning of graphical? It's not practical. Practically, these analysis cannot be done. These are all the theoretical analysis only. So now, you see, what is the first application? Seepage loss rate or flow rate. Number 1, seepage loss rate represented with Q. Seepage loss rate represented with the Q. So now if you observe, let me take what are these lines? Flow lines. And these lines are equipotential lines. So let me take a flow field. Whatever the flow field I have been explained over here. You know this flow field, right? I am taking the same flow field over here. So this is a flow channel, and each flow channel has the same discharge. See, there are there are 4 flow channels, right? And each and every flow channel has the same discharge. If I say first flow channel has a 10 meter cube per second, all the remaining flow channels also have same 10 meter cube per second. And the cross section area of this one is going to be delta B, and the length is going to be delta L. So now, you know the conditions of the flow net are what are the conditions of flow net we have been discussed? Q is equals to NF into NF into delta Q. H is equals to ND into delta H. See, you know that Q is equals to KIA. Yes. And now, as it is a small flow field, then delta Q is equals to K. K cannot be delta because K is a quotient of permeability. For small element or for large element, permeability is the same. So next, I. What is I? Head loss per unit length. This is one equipotential line and this is one equipotential line. Between our 2 equipotential lines, what is the head loss? Head drop. And over a length of how much? Delta L. So can I write I as delta H by delta L? Because these are 2 equipotential lines. These are 2 equipotential lines. Between any 2 equipotential lines, there is a drop known as delta H. Into, when the flow is happening in this direction, then what is the cross section area? Delta B perpendicular to the board 1. See, this is a flow and the cross section area should be delta B perpendicular to the board, which is going to be 1. Perpendicular to the board, which is going to be 1. So now delta Q is equals to K into delta H by delta L into delta B into 1. Now from this, you see, can I write delta Q as Q by NF? Q by NF is equals to K into, from this, can I write delta H as a H by ND? Yes, H by ND into delta B by delta L. So Q is equals to K into H into NF by ND into delta B by delta L. Delta B by delta L. So I told you the ratio of the dimensions of any flow field should be same, which means delta B by delta L is going to be constant for any flow field. So generally, flow field can be any shape. The flow field can be any shape. But for analysis, we assume as square, which means delta B by delta L is equals to 1. When delta B by delta L is equals to 1, then what is the final equation you are going to see? The final equation is Q is equals to Q is equals to K into H into NF by ND. This is the final equation we are going to get. Q is equals to K into H into NF by ND. See, I use the same form from Q Kia, but finally I have ended with the what? K into H into NF by ND. And you know what is H? Difference between the water levels. And what is K? Permeability. But instead of I, you see now, instead of I am using whom? Flow net. So what I have done is, I just manipulated the equation by using the flow net characteristics. And now instead of I am taking it as a NF by ND, where NF by ND is known as shape factor and depends on boundary conditions only. See, it won't change if the soil changes. It depends upon the boundary conditions. Now, one more point I want to mention over here. While I was discussing, did I mention the soil is going to be some clay? Did I mention the soil is sand? No. Flow net can be drawn to any soil mass. So the flow net does not depends upon the soil. The discharge depends upon the permeability. But this flow net property is NF by ND. What is mean by NF? Number of flow channels. And ND, number of drops. It depends upon the boundary. See boundary conditions. The lesser the boundaries, the lesser the NF by ND. The more the boundaries, the more the NF by ND. So NF by ND is a shift factor which depends on the boundary conditions only. This is a very, very important equation in this chapter, and based upon these equations only, there are a lot of questions have been asked earlier. So please have a look once. What is a boundary, sir? Boundary conditions means, you see, base of the dam, this is a dam or ground level, and this is going to be the hard strata. See, the boundary means the flow space where the flow is going to be happen. This is the space where the flow is going to be happen. If these boundaries are going to be near, then the flow space would be less. Sir, how area is delta B into 1, sir? Sir, what is the cross-section area, sir? How many times I say, sir? You please see, sir. Again, I'm going to represent for the sake of you people. You see, this is a flow, and I told you this is a delta B, and this is a 1. This is 1. Now, can you please tell me what is the area over here? What is area over here? Area is nothing but cross-section area is over here, delta B into 1. Now, you see the seabase pressure. Next one. Coming to the second one, seabase pressure. So, in the case of seabase pressure, yes, on this formula there are a lot of gate questions, and in this chapter there is a only means equation. Remember this, that equation. You see here, see the units are going to be meter cube per second per meter, right? Why, sir? You see, what is the units of the K value? Let's take meter per second, and this is meter. Then is there any units over here? No. What is the meaning of over here? Meter cube per second per meter. Per meter means per unit length of dam. Because you don't know the length of dam, right? Do you know the length of the dam? No, you don't know the length of dam. Sorry, you don't know the length of the dam. So that's the reason why I told you per unit of meter. That's the reason why I took this one as a delta B into 1. You see 1. What is the meaning of 1? The length of the dam is going to be 1. Now, coming to the next one. Second one is seepage pressure represented with the PS. See, when you are discussing about the seepage pressure, keep that in your mind. You go back. What is the seepage head here? H. Now, everybody, you have started with a H over here. Now, my question for you, do you think the seepage head at this point is the same as H? I have explained n number of times. Seepage head means array energy with which the flow starts. Now initially the energy is H. As you move, the energy will be losses. So now as the point changes, the seepage head is going to be changes or not. So let me take a point somewhere over here as A, and I am asking you the seepage pressure at a point A, which means you start with a seepage head of H. Then when you move, by the time you reach A, you will lose some head, and the total seepage head minus that head gives the seepage head at A. I hope you remembered yesterday's and day before yesterday's class also. Everywhere seepage head at section, some section is total seepage head minus head loss. So yet A, I'm taking the point as A. See, you know that PS at A is equals to gamma W into seepage head at A. The HS of A is balanced or remaining hydraulic or seepage head. So which is equals to total seepage head minus head loss up to A. Total seepage head minus head loss up to A. So what is HS of A? HS of A means total seepage head H minus head loss up to A. So now here the point is in order to find out the seepage head, first of all you need to find out this head loss at A. So how to find out the head loss at A? Earlier we know that head loss at any section is nothing but I into length up to that section. Yes or no? This is the formula that we followed earlier to determine the head loss. But now my question is, do you know the length of seepage from the starting point to A? Do you know the length? Do we know the length? No, I don't know the length. As I don't know the length, I cannot use this formula. So now how to find out this one? For this one, what I am going to do is from H is equals to ND into delta H, can I find out each drop is equals to delta H is equals to H by ND. What is the meaning of delta H? Delta H means each drop or not. Now the physical meaning of this delta H. Come on everybody. How many number of drops are there over here? 10. And what is the total head loss or what is the total head loss at the end? H. At the end, total head loss is going to be H. H to 0. Head loss is going to be H. And how many drops you taken? 10 drops. And as you know, you see, each drop is going to be same. Each drop is going to be same. Total head loss is equals to total drops into each drop. So can I say for 10 drops, it is going to be H. And for one drop, what is the head loss? For 10 drops, the total head loss is H. For one drop, H by 10. Can I say now delta H is equals to H by ND. What is ND? 10, right? So each drop is going to be 1 by ND times of the total head loss, or delta H is equals to H by ND. Now I want to know from the starting point to this point A, what is the head loss? Now let's find out how many number of drops are there. 1, 2, 3, 4, 5, 6, 7 drops are there. Yes. So for one drop, you know the value H by ND. Now how many drops are there? 7 drops are there. Then what is the total head loss or head drop up to A? Is total number of drops up to A into each drop. So I can write this one as HA is equals to N into delta H. HA is equals to N into delta H. So where HA is equals to N into H by ND. You don't need to remember all these things. So you just remember this value. You just remember this value. So how to find out head loss at any section? Where n is number of drops up to A. From figure, n is equals to 7. From figure, n is equals to 7. So once you know the head loss, then you can find out the seepage head at A. And if you know the seepage head at A, then you can find out the seepage pressure. My whole intention here is how to determine head loss at any point A, which is nothing but I want the total loss over here, which is nothing but how many number of drops are there up to this point? 7. So 7 drops into each drop as delta H. So if you understand this one, then total minus head loss up to that point, remove, you can get the seepage head at A. Now, the third one is uplift pressure or pore water pressure represented with a U. See, what is this uplift pressure? Come on. You know, the uplift pressure, see when the flow is going to be happen, you observe, means when the flow is going to be happen, this flow will exert an upward pressure over here. I hope you can understand this. This is nothing but uplift pressure or pore water pressure. Uplift pressure or, sir, what is the reason behind taking 7 drops? Arey, ab kaha re bhai? From where you people will come, re? What is the reason behind that? You see here, what is this? What is this point A? How many number of drops are there up to this point? I repeated that point 5 times. And now you are asking what is the reason behind the taking 7 drops? Yes? It's not assumption of 7 drops. You see A clearly. I hope this is visible for you. And how many drops are there up to A? Up to A. How many drops are there? 7. If I would ask you somewhere over here, up to this point, how many drops are there? 4. So from the figure I told you here, from the figure, n is equals to 7. I did not take it as assumption or I did not say it as some reason. So now, you see, okay, so generally we take the downstream level as a datum. We take the downstream bed level as a datum. Generally, we take the downstream bed level as a datum. So now you see there is an uplift. Does the uplift happen somewhere below the soil mass or beneath the dam? What is meant by uplift pressure? A pressure applied at the base of the dam to lift up the structure. Uplift pressure means to lift up the structure. So that will be present over here only. Yes. Now, so let me take this is the uplift pressure. Okay. Let me take a point C. This is a point C. Let's take the point C and this is the point A. And if you observe, point C and point A both are lying on the same equipotential line. What is this line? This is equipotential line. This is equipotential line. Now everybody see, this is our datum. Yes. Now the point is below the datum. When the point is below the datum, let's say the datum head is going to be Z. You know that when the point is below the datum head is going to be negative. When the point is below the datum head is going to be negative. So now my question is, at this point, what is the pore water pressure? Let us see. Sir, why you are taking at C only? Can I take here? Yes, you can take here. You can take here also. But I am taking this one for just understanding, to make you understand. Sir, can't I take the point C over here? Can't I take the point C over here? No, because uplift happen beneath the dam, just below the dam. So uplift happens just below the dam, which means you have to take the point at the base of the dam. Now, uplift pressure U is equals to gamma W into HP, means pressure head at C, where HP is pressure head at C. Now, you see, if this is the datum, if this is the water level, then what is the total energy over here? This is the total energy. And what about the total energy over here? This is the total energy. So whatever the total energy here is T1, and whatever the total energy here is T2, and what is H? T1 minus T2, which means the difference between the two water levels. So now, if I would have kept in a piezometer, if this is a dam, I need to find out the pressure head at C. How to find out the pressure head at C? You see, this is initial water level 1, this is final water level 2. Now, at this point C, if I would have insert a piezometer, up to what height water level rises? You please tell me. You please tell me. See, this is the water level. This is the water level. So now, if I insert a piezometer, definitely at this point, if I insert a piezometer, this is water level, this is water level, somewhere in between, this is a water level. Yes or no? I hope you understood the meaning between the hydraulic gradient line. I hope you understood the meaning between the hydraulic gradient line. This is a Pehle water table 1. This is final water table 2. In between, somewhere over here, this is a water table or not? Now, how come I find out this one, sir? See, so if I insert a piezometer over here, means I'm not really inserting over here, I'm showing you for the sake of explanation. Then the water level will rises to somewhere over here. Then the water level will rises to somewhere over here. And whatever, this is nothing but head loss up to C, and this is nothing but pressure head at C. Whatever, this is nothing but a head loss up to C, then this is going to be pressure head at C. So what is this pressure head at C, sir? Now, from figure, pressure head at C is equals to, you see, this is value T1 from this top to the bottom. What is the value? Please observe. T1 plus Z. T1 plus Z. T1 plus Z minus head loss up to C. Minus head loss up to C. So T1 plus Z minus head loss up to C. That's going to be the uplift pressure head. This means pressure head means piezometer. So how to determine this HP of C? T1. This is a T1 plus Z minus HC. This is how you need to find out the value, where HC is head loss up to C. And what is HC again? N into delta H. Just now I mentioned na head loss. Where N is number of drops up to C. You go to the figure again. You go to the figure. So how many number of drops are up to C? You please see, as a point A and a point C both are lying on the same equipotential line. Point A and point C both are lying on same equipotential line. Then definitely the number of drops are going to be same. N is equals to 7 from figure, because I took as point A and C lies on same equipotential line. Same equipotential line. See, these things we discussed earlier. Now, what you need to know here is how to determine the head loss. Earlier, we used to find out the head loss. How? Hx is equals to I into length of 2x. Now, I am not going to use any I or length. I just simply find out the each drop. How? Delta H is equals to H by ND. And I can find out the number of drops up to that point N into delta H. That's it. So now the last one. Exit gradient I exit. Mr. Salim, what if the point doesn't lie on the line? Very good question. See, I have taken the points exactly on the line. If the point lies over here or if the point lies over here, you have to consider the means you need to go for the graphical procedure and you have to check by using area volume techniques. That's the reason why I told you those are highly means this fluority is a highly graphical procedure which you cannot measure the values directly. So if they would have given the point somewhere over here, now 6 drops full and 7th drop as a half or partial, and that will be discussed by doing some rigorous analysis, and that is going to be for the PG post graduation level, not for UG. So you don't need to worry about that. In examination, if they ask, they will ask you at the lines only, not below or above the line. To plot a graph, we need pressure on every point. Yes. Now coming to the exit gradient. Sir, what is this exit gradient? Now, I hope you remember the piping failure. So where does the piping failure occurs? Please everybody tell me. Piping failure occurs means think. Piping failure occurs on the downstream side or on the upstream side? On the downstream side. I told you yesterday, piping failure starts on the downstream side and progress to the upstream side. So piping failure starts on the downstream side and progresses towards the upstream side. See, this is very, very important. This formula is going to be very, very important. Q is equals to K into H into NF by ND. So now you tell me. Piping failure starts on the downstream side and progress towards the upstream side. And if there is a failure at the outside, means exit point, exit means on the downstream rod or not. If there is a failure on the exit, then definitely that soil erosion will progress towards the upstream. So if the soil is safe on the exit, then there is no soil erosion towards the upstream. But if the soil is going to be fail on the downstream side, then definitely there is going to be failure towards the upstream side. So that is the reason why we take it as an exit gradient. Exit gradient. So what is this exit gradient, sir? Now you observe. These one, I just represented these values over here. This is a dam, Nana, and this is going to be the flow line. So whatever this is nothing but you see this value, this is going to be exit flow field, and flow will take place like this. Yes or no? So flow will pass us through here, and this is going to be the downstream water level. So in the case of the exit flow field, now whatever the drop here to here, this is equipotential line, whatever the drop is going to be same. So I exit is equals to the head drop between any field is going to be same. But you see, whatever the length we are going to mention over here on this length, this is going to be delta L at exit. This will be given for you. See, all these things will be provided after doing the flow chart or flow means a flow net. and you are not going to be do anything over here in the field engineers is going to be provide this flow net for us, and once we get the flow net, from the flow net you see this is the flow field or not, whatever, this is nothing but I'm drawing over here exit flow field. So this exit flow field I have taken over here, and I have mentioned this is a delta L at exit. So what is I exit? Each drop. How to find out each drop? How to find out each drop? Total head loss by number of drops. You see how to find out each drop? Each drop is going to be find out delta H is equals to H by MD. So once you know this one, then we can find out the I exit. Once you know the I exit, then factor of safety against the piping. In the previous chapter, IC by I mentioned you I. In the previous chapter, I mentioned you I. Now I am going to write as I exit. Because in the previous chapter, there I have taken the I where? On the downstream side for the upward seepage only, right? Here also I am taking the same thing, but I am giving a name as I exit. Some of the student ask, sir, I and I exit both are same. Yes, I and I exit both are same. So now this is the factor of safety against piping. IC by I exit, where IC means critical hydraulic gradient. So generally, factor of safety is kept as a 4 to 5 against piping. Generally, we keep the factor of safety as 4 to 5. So this is about the flow net and how to determine the seepage. See, the only definition, only derivation is this one, and remaining these things are small things only. Can't we discuss? Haven't we discussed all these things earlier? We discussed, but the point that I mentioned clearly here is newly HEC or HEA is equals to N into delta H. Sir, is delta L is same for every flow field? No, sir. Delta L is not going to be same. Delta B is not going to be same. Sir, is this topic important? Yes, this is very important for the GATE examination. I'll show you. Most of the questions in this topic, most of the questions will be appeared from the Q is equals to K into H into NF by ND only. So that's all. How will you plot the graph? Arey Baba, you don't need to plot the graph, Baba. How many times I say you please worry about what you need to do, but not what you don't need to do. What is hydraulic gradient? My dear student, sir, what is hydraulic gradient? Wow. So you please go through the previous class videos. I hope you have joined today's session only. So you please go through the previous videos, and if you go through the previous videos, you will getting to know that. Sir, but you told B by L is equals to 1. Sir, I told you that this is delta B by delta L, sir, and for the analysis, we assume it is a square, sir. The square means, you see, there can be smaller square and larger square. Small squares would be there and large squares would be there. And make sure that flow field, the delta B by delta L is constant, not a flow field constant. Delta B by delta L, the dimensions are going to be constant. Sir, your teaching is best. Thank you, Mr. Raviraj. Thank you. Sir, is the area of every flow field is same? Mr. Harshavardhan, just now I have discussed area of flow field is not going to be same, but the ratio of delta B by delta L is going to be same. Okay. So please keep that in your mind. Sir, why sheet pile at upstream side? Sir, you can provide the sheet pile on the downstream side or middle holder, sir. Just for the sake of explanation, I have taken this one, sir. Sir, sir, if you got IIT level marks, then why are you teaching? No offense, Mr. Charan. So I got IIT level marks, but my passion is towards teaching. That's the reason why I joined a teaching, and I don't teach in colleges. I do teach only in the ACE Institute. There is a premier institute, and I told you I was a student of the same ACE Engineering Academy. And at the time only, I thought of like to be in a part of this ACE faculty. So after my MTech, I directly joined into the ACE Academy. I mean, I got jobs. I got L&D placements in my BTech, and I got a L&D in my MTech also. After completing my MTech also, I got a L&D. So I got a job offer from the L&D, and I got a job offer from the Kalinga University, the people who are staying in Odisha. So they will be know that Kalinga University, and I have got one more university in the Hyderabad itself. But I did not opt for the university or L&D. I joined in the ACE Engineering Academy. So I mean, those things. Why not PSUs? For the rank I got, and I am under open category OC. So for the open category, in the case of, I'm telling, I want to say one more point over here. And the people who are open categories out there, if you want to join PSUs, you have to get a rank a minimum 250. 250 is the benchmark for you. All India rank 250 is the benchmark for you for the open category students. If you want to join the any PSU, so you know the lot of PSUs are there. IOCL is there, Indian Oil Corporation, BHEL is there, Navratna, and ONGC. So there are a lot of PSUs, you know that. So for each and every PSU, if you want to go for the apply separately also, rights is there. And for those PSUs, if you want to go for that, means if you get a job, the minimum rank you require is 250. So my rank crossed 600. So I'm as I'm an open category, I did not got any PSUs. Okay, fine. Yes. Now that's all about the conditions. So this is I exit. I exit means delta H. What is the delta H over here? Delta H means H by ND. And whatever the length of the flow field here, delta L at exit, they will be given. So you can find out the factor of safety. Generally, for safety means design, Nana. When F equals to 1 critical condition, for safe design, we provide the factor of safety as a 425. So now, yes. Okay. Stop. Flooding me the messages. And now, see, note. A flow net characteristics and applications are useful for isotropic and homogeneous soils. Isotropic and homogeneous soils only. So flow net characteristics, whatever the characteristics I have discussed, because you see the starting point, how I have got this one. What is this? You please look over this Laplace equation. So in the case of Laplace equation, for isotropic, I took it as a Kx is equals to Ky. Then flow lines, and this is the flow lines, this is the equipotential lines. From this only, I started the characteristics. from this only I explained the applications, which means so far whatever I have done is for soil is homogeneous and isotropic. Now, what we have to do in the case of anisotropic soils. But in reality, what is the type of soils we are going to see? In reality, we have to use means in reality the soils are anisotropic soils. So now let's go for the anisotropic soils. For anisotropic soils, I hope you remember the meaning of anisotropic soils are stratified deposits. And you know, Kx of the soil is greater than Ky, which is a Kx. What is meant by Kx? Average permeability when flow is parallel to bedding planes. Ky, average permeability when flow is perpendicular to bedding planes. If you have any doubt regarding to Kx and Ky, you please refer the video and PDF of chapter number 6 permeability. There I have been discussed very clearly how to determine Kx and Ky, and we have solved the problems also. Now, for anisotropic soils, the Laplace equation is Kx into dou square h by dou x square plus Ky into dou square h by dou y square is equals to 0. So now, in order to apply flow net characteristics, first, in order to apply the flow net characteristics, Laplace, this equation, soil should be converted from anisotropic to equivalent isotropic nature. Equation should convert from anisotropic to equivalent isotropic. So how it is going to be possible, sir? Now, you please observe here. What I am going to do is I have to convert this equation into equivalent isotropic. What is the isotropic equation? The isotropic equation is going to be this one. This is the isotropic equation. Now I have to convert that into equivalent isotropic equation. How it is going to be possible? So what I do is divide with Ky on both sides. If I divide with Ky on both sides, now you see here Kx by Ky. Kx by Ky, can I write it as 1 by Ky by Kx into dou square h by dou x square plus 1 into dou square h by dou y square is equals to 0. So first let me write down normally and then I will write down because again people will ask me Kx by Ky. So divide with the Ky on both sides. Now I can write this equation as 1 by Ky by Kx into dou square h by dou x square plus dou square h by dou y square is equals to 0. Dou square h by dou y square is equals to 0. See now, if you observe, does the second form is exactly equals to the second form of isotropic equation or not? So what is the second form of isotropic equation? Dou square h by dou y square. And what about the second form of this one? Dou square h by dou y square. So now what I do is let's say x square is equals to Ky by Kx into what I'm going to do is x dash square is equals to Ky by Kx into x square. You see what I am taking is this entire into one single form. Some just like in mathematics we do take, right? X into y into z is equals to, let's assume as a. x into y into z, or let's take some complex variable as some simple a or b. We're going to take some assumption, right? See, don't ask me why you're taking like this, sir, because I am just taking that this value is going to be in terms of x dash. Now, if I apply the partial derivative on both sides, if I apply the partial derivative on the both sides, now if you see, the partial derivative means dou x dash square is equals to ky by kx is going to be constant into dou x square. So can I rewrite this equation dou square h by dou x square 1 by ky by kx into dou square h by dou x square plus dou square h by dou y square is equals to 0. Dou means partial derivative nana here. So then ky by kx into dou x square can be written as dou square h by dou x dash square plus dou square h by dou y square is equals to 0. Now, how does this equation is going to be looks like? This equation is going to be exactly looks like, see, this is the anisotropic equation I have taken. Yes or no? This is the anisotropic equation I have taken. And now this is the equivalent isotropic equation I have taken. See, what I have done is simply the convert from the anisotropic to equivalent isotropic. See, this is going to be the equivalent isotropic. This is equivalent isotropic. So, how I have convert the equivalent isotropic? How I have convert the equivalent isotropic? The base dimension x dimension, the base dimension x dimension is going to be reduced to x dash. So you see here as x dash square is equals to ky by kx into x, then x dash is equals to root of ky by kx into x, which means, look everybody, the final conclusion I want to say over here is, how come I write this anisotropic equation into isotropic equivalent isotropic equation? By changing the x to x dash. Yes or no? By changing the x to x dash. And what is x dash? X dash is equals to root of ky by kx into x. Sir, as you know, kx is more than ky, then ky by kx, denominator is more and numerator is less. So denominator more, numerator less, the total value is going to be less than 1. Can I say the x value is more than the x dash or not? Because root of ky by kx is less than 1. Definitely, as kx greater than ky, root of ky by kx is less than 1. So which means x dash is equals to lesser value into x. So now where root of ky by kx is equals to reduction coefficient. Reduction coefficient. So now finally, what I am going to do, see, this is an equation. From this equation, I have made sure this equation. What is the actual meaning of this one, sir? The meaning of this one is, for applying flow net characteristics, for applying the flow net characteristics, anisotropic nature is converted to equivalent isotropic nature Array, if you have any common sense of you people, I did not complete this. So I did not complete the topic. So meanwhile, you don't poke me. If you have common sense, listen first, complete. Let me complete that, and then I'll discuss. And meanwhile, while something is going on, while I was writing plus x only, you are asking me, sir, what is y? Is converted to equivalent isotropic by transforming the base length x to x dash using reduction coefficient. So reduction coefficient root of ky by kx. So which means if you want to convert it, you must have to convert into equivalent isotropic. How you are going to change it? By reducing the base length as x to x dash by using a reduction coefficient. See, if I write this one only, then the form is going to be equivalent isotropic. So now let's see how it is going to be applied practically, sir. See, this is the actual dam, and let's say this is the upstream bed level, and here it is the downstream bed level, and you see yes. See, what is this base width? B, and this is the ground level, and let's take the total thickness of the soil sample is D. This is anisotropic soil, Anna. What is the meaning of anisotropic soil? In x direction, kx, in y direction, ky. So permeability, this is a anisotropic soil mass. But can we apply the flow net characteristics directly here? No. This is anisotropic nature. So you have to convert into isotropic nature. Now how? Transformed section. Have a look over here. How we are going to transform the same thing. So what we are going to do is by reducing the transforming the base length x to x dash using a reduction coefficient. Now you tell me, does this value and this value both are same? Now this is a small b, and you see the thickness of the soil is going to be same because we are not changing any depth dimension. Can you change the depth dimension over here? No. Can you remove the soil mass? No. So what I can do is, see, this base width is in my hands. This base width is in my hands. So as it is in my hands, means as an engineer, see, this depth cannot be changed. This depth is not going to be changed. As this depth cannot be changed, what we can do is we can reduce the base length from capital B to small b. So now once I transform this, now you please tell me, see, this is a capital B and this is going to be small b, where capital B is original width and small b is transformed width. And what is a small b here, sir? Then this small b is equals to root of ky by kx into capital B. So this is the final formula. What we are going to do is, if you want to apply the flow net for an anisotropic soil, first of all, you have to reduce the base length of the dam from capital B to small b, because who is x dimension over here? B. Who is the y dimension over here? D. We cannot change the thickness of the soil. But we can change the width of the dam or not. So now, as we change the width of the dam, now I can apply the flow net over here. You please apply, see. Now I can apply the flow net over here. You observe. This is one flow line. This is one flow line. This is one more flow line. And I can draw the equipotential lines. This is a one equipotential line. This is one equipotential line. 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 And this is also one more equipotential line. So you see, you are not going to be apply the flow net directly to the given dam. You are going to be converted the given dam from capital B to small b. So after transforming this only, then only we are going to see transformed section. So now you please tell me how many number of see, this is nothing but the difference in the water levels that's there. The difference in water levels would be same. The difference in the water levels would be same. So once we draw the flow net, can we number out how many number of flow channels are here? I hope you can say, see, this is a flow channel number 1, flow channel number 2, flow channel number 3, flow channel number 4. So NF is equals to 4. And how many number of drops are there? 1, 2, 3, 4, 5, 6. And how many number of drops are there? 6. Then how to determine the discharges are? What is discharges are? K into H into NF by ND, sir. Sir, once I draw the flow net, sir, can't I get down the NF and ND? Yes. What is the H? The difference between the water levels? Yes. But what about K, sir? K is going to be KE, effective permeability. So now, what is this KE is? This KE is a geometric mean of the KE is going to be geometric mean of the both horizontal permeability and vertical permeability. So this, for applying the flow net characteristics, you please observe this point, understand this point clearly. For applying the flow net characteristics, anisotropic nature is converted to equivalent isotropic by transforming the base length x to x dash using reduction coefficient root of ky by kx. What is the base length? Capital B. Reduce it to small b by using root of ky by kx. So once we reduce this base section, then only we are going to apply the characteristics. This is an equivalent isotropic, and this is anisotropic. So that's all. See, the only change here is you need to reduce the base width, then you apply the characteristics, and the same formulas are going to be applicable. Same formula. What is the same formula here? So K becomes KE. What about seepage pressure? I started with H. Somewhere over here, if I want a seepage pressure at this point, total seepage head minus head loss up to A. How to find out head loss up to A? Each head loss is nothing but each head loss delta H is equals to total head loss by number of drops. Then up to A, how many number of drops? 3 drops. 3 into delta H. The only change is this one, Nana, K becomes KE, where K is equals to root of KX into KY. But in order to apply this one, you have to reduce this one. So that's all. and we'll see one gate question regarding to this one, and then we'll stop today's session. And today I'm going to give you assignment for chapter number 8 and for chapter number 7 and for chapter number 8. At evening I'll give you the assignment problems. So I'm giving you some time, so I'm not going to take any doubt clearing session today also. Why? Because I want you to people, I'm allowing you people to go to the home and look over the notes once again. So whatever the doubts you have, I'll be taking that session tomorrow, because after 9th chapter, once the 9th chapter also ends, then we can complete the entire series. So I will allow you to discussion the doubts section tomorrow or a day after tomorrow. I'll allow you, so that we can take a 1 hour to 1.5 hour session also, so that I can clear you all of your doubts. So now let's solve some previous gate question and IS questions. Okay, fine. The people who will leave means if you want to leave, you can leave, but it's up to you. So if you want to look over the problems and if you want to discuss some questions, then it's up to you. Because I don't want to stop for anyone. So it's been 16th day. So now let's go for some questions. Meanwhile, let me save all these things. Okay. So now we have saved those things. Let's see. Yes. So now you see everyone. Yes. See, this is the chapter number 9. Previous gate questions I am showing you. I hope you can able to see this one. So previous gate question, this one, gate 2 marks question. A flow net beneath a dam consists of 24 equipotential drops. What is the meaning of 24 equipotential drops? ND 24. Number of flow channels NF as 7. The difference between upstream and downstream water level is 6 meters. What is the difference between upstream and downstream water level? 6 meters. The length of the flow line adjacent to the toe of the dam at exit. What is the meaning of this one? You see, this is a dam and this is going to be the flow line, right? So whatever the flow line, the length of the flow line adjacent to the toe, this is a toe of a dam, at the exit is going to be 1 meter. So this is the length of the flow field. They have given delta L exit is given as 1 meter. I told you they will provide you in the examination. Specific gravity and void ratio. The specific gravity is given as 2.7 and void ratio as 0.7. Factor of safety against a pipe. So what is the factor of safety against piping? So for finding the factor of safety, you don't require NF or India or something else. But now you see how to find out the factor of safety. What is the factor of safety? IC by I exit. IC by I exit. So you know that IC is equals to G minus 1 by 1 plus E. So IC is equals to 2.7 minus 1 by 1 plus 0.7. Directly I can say IC is equals to 1. And what about I exit, sir? I exit is equals to delta H by delta L at exit. Yes. So what is delta H? Delta H means total head by number of drops. In simple language, I am telling you, array total head means total number of drops. For total drops, ND, total head loss H. For one drop, how much? For one drop, single drop delta H, total head loss or hydraulic head by number of drops. So what is the total head difference they have given? 6 by what is the number of drops they have given? 24. So 6 by 24, 6 by 24, which is going to be 1 by 4, keep it aside. Then I exit, I don't want to use any calculator. I exit is equals to delta H 1 by 4 by delta L exit 1. So 1 by 4 into 1, which is going to be 1 by 4. Then what is the factor of safety? What is the factor of safety? IC 1 by 1 by 4. The answer is going to be 4. Answer is D. I hope you understood over here. Simply, I am asking you to find out the factor of safety. What is the factor of safety? IC by I exit. So, as they mentioned, the I exit means delta L at exit. I can find out the delta H. How to find out the delta H? Total drops means total head loss by number of drops. Sir, I said factor of safety is going to be in between 4 to 5, but that doesn't mean that in the given options it is going to be present over there. Sometimes it can be 3 also. Generally, in engineering aspect of view, we design for a factor of safety 4 to 5. That's the range. Now, I hope you have copied or taken this one also. I hope you understood. Now I'm going for the next question. Now you see, a sheet pile has an embedment depth of 12 meters in a homogeneous soil mass. A sheet pile has an embedment depth of 12 meters in a homogeneous soil stratum. The coefficient of permeability is 10 to the power of -6 centimeters per second. See, so far we have been discussed about dam, right? Now I am going to construct a sheet pile wall. See, sheet pile wall is also going to be used to store the water. Now, this is a sheet pile wall. This is a sheet pile wall. So, what is the permeability of the soil mass I have given? With into a homogeneous soil strata, the permeability is given as 10 to the power of -6 meters per second. Difference in the water layers between two sides of the sheet pile wall. What is the difference in the water levels? The difference in the water levels they mentioned as H is equals to 4 meters. The flow net is constructed with a 5 number of flow lines and 11 number of equipotential lines. See, they have constructed a flow net beneath this. So number of flow channels is nothing but number of flow lines minus 1. So what is the number of flow lines I have mentioned over here? 5 minus 1. Sir, did they mention this one with respect to the boundary conditions? Yes. When they say number of flow lines, which means they included all the boundary conditions also. Then what is the number of drops, sir? What is the number of equipotential lines I have given? 11. So number of equipotential lines minus 1, which is going to be 11 minus 1, which is going to be 10. Then what is the quantity of seepage in centimeter cube per second per meter? See, first we'll find out the seepage. What is seepage? Q is equals to K into H into NF by ND. So here, what is the K value given? 10 to the power of -6. First you will find out in terms of meter cube only. 10 to the power of minus 6 into H 4 into NF 4 by 10. So what is this value? 4 4 16. So 16 into 10 to the power of minus 5 meter cube per second per meter. 16 into 10 to the power of minus 5 meter cube per second per meter. See, they have given equipotential lines. Now 4 4 16. So 16 into 10 power of minus 5. But they're asking in a centimeter cube per second or not. You know that 1 meter cube is equals to 10 to the power of 6 centimeter cube. So now can I write 16 into 10 to the power of minus 5 into 10 to the power of 6 centimeter cube per second per meter? Then answer is going to be 160 centimeter cube per second per meter. Okay, sorry. This is a 10 to the power of minus 7, right? I'm sorry. This is 10 to the power of minus 7. So 10 to the power of minus 7 into 10 to the power of 6, which is going to be 1.6 centimeter cube per second per meter. So yes, this is the value. That's it. I save this. Now this will be discussed tomorrow. See, this is also anisotropic soil mass. I must have discussed there only, but let it be. We will be discussing tomorrow that one. Now, you see, this is a figure. You observe the flow net constructed for the dam is shown in the figure, taking the coefficient of permeability. What is the coefficient of permeability? 3.8 into 10 to the power of minus 6 meter per second. Quantity of flow in centimeter cube per second under dam per meter of the dam. So they are asking Q in terms of centimeter cube per second under per meter of dam. So now you see this. If you observe, first of all, in this, what is the discharge? Q is equals to K into H into NF by ND. Q is equals to K into H into NF by ND. So now if you observe over here, first of all, what is K value? Yes, K value is there. And what is H value? You see, this is water level and this is water level. The difference between these two water levels here is 6.3 meters. So the difference between water levels given as 6.3 meters. And now you need to find out the NF and ND. So first of all, fix out NF and ND over here. So how many number of flow channels are there? Number one flow channel. Number two flow channels. Number three flow channels. Because flow will take place here, here, and here. Means flow takes place here, here, and here. So how many number of flow channels are there? 1, 2, 3. So NF is equals to 3 from figure. We have to fix it. NF is equals to 3. And now, how many number of drops are there? Between any flow lines, you can see this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total how many number of drops are there here? 10 drops are there. And total how many number of flow channels are here? 1, 2, 3. 3 flow channels are there. So number of drops are going to be 10. Then find out the discharge first in terms of the meter cube per second. Then we can find out in terms of centimeter cube per second. See, in this question, Q is equals to K value 3.8 into 10 to the power of minus 6 into H value 6.3 into NF 3 by 10. So definitely you have to use the calculator. So no other option over here. So please look out the calculator. 3.8 into 6.3 into 0.3, which is going to be 7.182 into 10 to the power of minus 6 meter cube per second per meter. 7.182 into 10 to the power of minus 6 into 10 to the power of 6 meter cube, centimeter cube per second per meter. So they are asking centimeter cube per second under a meter, dam per meter of the dam. So per meter of the dam means per meter over here. So now what is this value? 7.182. As they did not mention anything, see, did they mention any rounded to 2 decimals? No, they will definitely give you the range. The range would be 7.18 to 7.19. The answer. Actual answer given as 7.18 to 7.19. So this is the final answer. Now, if you observe, see, is all the questions I have explained either by means of factor of safety or by means of the discharge. What I want you to observe over here is in this question, they gave a flow net. They directly give the flow net. From the figure, I can find out NF and ND. So if you have go through this question. If you have gone through this question, in this question, what they mentioned is a number of equipotential lines and number of flow lines. Either they will give you the flow lines and equipotential lines, or they will mention the figure also. So these are some of the previous gate questions. The unit of K. So what is the problem? Okay, so that's all with this one. And now, see, these are the gate questions I have been discussed. I have shared, I have saved everything. I'll be sharing with you now. These are some of the previous IS questions. So, if you see, a flow net is drawn. These are previous IS questions. Yes. See, a flow net is drawn to obtain seepage, quotient of permeability, and uplift pressure. Yes. See, we have find out the seepage Q, and we have find out the uplift pressure U. But have you find out the quotient of permeability? No. So this is not true, because quotient of permeability is not going to be found by using the flow net. Flow net does not depends upon the soil property. Flow net does not depends upon the soil property. Quotient of permeability, uplift pressure, and exit gradient. No. Exit gradient, uplift pressure, and seepage quantity. Yes. And exit gradient, seepage, and quotient of permeability. No. So you see, flow net does not depends on soil property and not useful to determine coefficient of permeability K. So this is the answer. The answer is going to be for this one, answer as a C. Now, this diagram we'll be seeing tomorrow. And now, yes, you please see this one. There is a previous IS question. There is also a previous IS question. You please observe. See now a flow net for an earth dam of impervious foundation. A flow net for an earth dam of impervious foundation consists of 4 flow channels and 15 equipotential drops. So how many flow channels are there? 4. How many equipotential drops are there? 15. So flow channels as a 4 and drops as a 15. The full reservoir is 15 meters above the downstream horizontal filter. So full water level means full reservoir means upstream water level is 15 meters above the downstream water level. So there is an earth dam, and see for this one there is no point of looking over earth or any other dam, but as of now you know the formula. The formula is going to be same for both earth dam and the gravity dam. So they have given the H is going to be 15 meters, given the horizontal permeability Kx as 9 into 10 to the power of minus 6 meter per second, vertical permeability Ky as 1 into 10 to the power of 6 minus 6 meter per second. Quantity of seepage through the dam, you see ml per second per meter, milliliter per second per meter. So first K into H into NF by ND, where K becomes Ke. What is Ke? Root of 9 into 10 power of minus 6 into 1 into 10 power of minus 6. So which is going to be, see root 9, 3 into 2 times of 10 to the power of minus 6, which is going to be 10 to the power of minus 6 only, because 10 to the power of minus 6 square, root will get cancelled, meter per second. Now Q is equals to 3 into 10 power of minus 6 into H. What is the H value given? 15 meters into 4 by 15. 15 will get cancelled. Then 12 into 10 to the power of minus 6 meter cube per second per meter. So now, can you please tell me what is 1 meter cube? 1 meter cube is equals to 10 to the power of 3 liters or 10 to the power of 3 milliliters. So now I can write this one as 12 into 10 to the power of minus 6 into 10 to the power of 6 ml per second per meter. So answer is going to be 12 milliliter per second per meter. Answer is D. So see, the point I want to explain you in this chapter is that discharge equation is very important. That's it. And sir, why you did not change the base width, sir? You don't need to, because already they have drawn the flow net, right? Once they've drawn the flow net and they have given the values, we don't need to worry about that. Okay. If you want, you can look over for a minute. Yes. You see, just now I explained this point, right? Flow net is dependent on the permeability of soil through which flow is taking place. Just now I mentioned you flow net is independent on the soil property. Flow net depends on boundary conditions only. The flow net is useful to find out the discharge. Yes. See, flow net is independent on soil property. The same question, assertion is going to be false, but reason is going to be true. So what is the correct answer over here? Assertion false, but reason is going to be true. Answer here is D. Answer is D. Now, okay. So let's see this question, please. This question. So they have given some statements and consider the following statements, and we have to say which of these following statements are going to be true. So yes, quantity of seepage in each flow net, quantity of seepage in each flow channel is independent of the size of the field. Yes, I told you whatever size of field for each flow channel delta Q is same. So this flow channel depends, see, the whatever the flow rate depends upon the flow channel. It does not depends upon the size of the field. So now is independent in each flow channel is independent of the size of the field. Yes, one is going to be correct one. Now as one is going to be everywhere, now can eliminate this one, 2 and 3 only. Drop in head between adjacent equipotential line of a flow net is dependent on the upstream head. Drop in head is drop in head between adjacent equipotential lines of a flow net are dependent on the upstream head. No, it does not depends upon the upstream head. See, the drop in head does not depends upon the between any two equipotential lines always head drop is same, which is independent on upstream head. So whatever the upstream head it may be, while it is flowing, the drop is going to be same. So as they have mentioned dependent, this is wrong. So now I can eliminate answers directly. So answer should be 1 and 2 should not be there. So to eliminate and eliminate. The correct answer is going to be 1 and 3 only. Now let's see. With increasing the length of a flow path, the corresponding exit gradient will decrease. Sir, why, sir? Sir, you see, sir, why? What is the exit gradient, sir? Delta H by delta L of exit. See, you see, if the delta L increases, then exit gradient decreases. So with increasing the length of the flow path, which means delta L increases, the corresponding exit gradient decreases. So the correct statements are 1 and 3 only. So answer is C. So the first one, quantity of seepage, irrespective of the field size, it is same. Second one, irrespective of the hydraulic head, I told you these are the two characteristics of the flow net. You must have to remember this one. So these are the questions regarding to the IES and GATE from this chapter. So some other leftover portion is there. We will see that in tomorrow. But today I'm going to give one more thing for you. You please go through the. Yes. So you please go through GT volume 1. You please go through GT volume 1. In that volume 1, I'm asking you to solve. Please keep this in your mind. Classroom practice questions. Question number 2. Question number 2. You please solve this question number 2. Question number 4. And question number 5, 6. 2, 4, 5, 6. Two, 4, 5, 6. Homework. Chapter 9. Classroom practice questions. Question number 2, 4, and what is that? Any other values? 2, 4, 5, 6. 5, 6. So you please try to solve these questions. We'll see the problems remaining and the topics tomorrow. So that's all with this today, and I'm not going to take any doubt clearing session today. So I'll be seeing the messages. I'm not going to raise or enable anything today. I'm giving time. So you please make sure. Today also we have discussed some topics, right? You please take some time. We'll be discussing the things and doubt clearing session tomorrow once the end of the chapter. So I'll give you a quick summary of 6, 7, 8, 9. So now the people who wants to leave, you can leave. Mr. Ketan, today I'm going to upload the PDF within 10 minutes after the class. Yesterday I told you I have a class in afternoon session, so that's the reason why it took time to upload the PDF. Have some punctuality, sir. How dare you to say to that to me? Have some punctuality. Am I doing any charity over here? Do you think am I doing any charity? Okay, fine. From tomorrow onwards, the class is up to 1 o'clock. And I'm not going to take any doubt clearing session because the class is sessioned up to 1 o'clock. Every day I am taking a half an hour, 40 minutes extra for the sake of you. And you have a dare to say to me that I don't have punctuality. Yes, fine. Mr. Kaushik, what is the exact use of exit gradient? I told you the exact use of exit gradient is to check whether the soil will undergo some piping failure or not. You please look over this one. Please look over this one. Once you know the exit, we can check whether this exit gradient is going to be less than IC or more than IC. Then we can check the factor of safety against the gradient. Yes, today's class is ended. So those who wants to leave, you can leave. I hope, Mr. Kaushik, you got your answer. Mr. Mona, upload the sample of how to prepare short notes, sir. I'll try to send it by today evening. Sir, an anisotropic soil delta Q must be defined. Anisotropic soil, I convert it into isotropic nature. When you convert into isotropic nature, then all the fluent characteristics and properties can be available. And I don't know, see, like it's really sometimes it will be irritate not only anyone after taking these efforts and taking the number of time means more time for you people, and you people and some of the people are saying have some punctuality. Yes. So IC is less than 1, that quicksand condition. See, when IC is less than 1, see, a given IC range is going to be 1. When IC is going to be less than 1, generally the quicksand condition is going to occur. The range of IC is more than 1. When IC is less than 1, quicksand condition occurs, Mr. Anonymous attendee. Can we use FlowNet to find a capacity of reservoir? Sir, the FlowNet is used to find out the seepage passing through the soil, not to find out the capacity of reservoir. Anisotropic means what, sir? You please go through the earlier soil. So my problem is I am preparing all the formulas, but when I see the question, I am unable to answer, sir. See, it's not about looking the formulas or by hearting the formulas. It's about understanding the nature, where to apply and where not to apply. Just because you mug up or you remember the formulas does not fetch you anything. So once you are reading the formulas, you try to please analyze how those things came. Most of the formulas I have given, I did not given you directly. I gave you the explanations also. One of our attendees, sir, delta H is a H by ND now, so then it depends on total head. See, they are not asking the magnitude. They are not asking the magnitude. They are asking between any two equipotential lines, does head drop is same or not, and does it depends upon the hydraulic head. See, that value may changes, but you take any successive equipotential lines, always the delta H is going to be same. Sir, in reality, it is possible to decrease in dam width. Yes, you are an engineer, right? It's up to you. While you are going to give a design, you can reduce the width. So what if Kx is less than Ky? See, Kx is less than Ky only in collapsible soils. That is a very rare condition. So it won't be happen. But most always 99% Kx is more than Ky. There is a proof for that also, but I don't want to discuss that proof and all those things. I don't want to take into different level. That is for the PGs, I can say, but it will be waste of time. So I did not give a discussion of a proof for that. So, but mostly the soil is Kx greater than Ky only. I'm going to give a summary of 6, 7, 8 tomorrow, not today. So your teaching is great. Fine. Thank you. Thank you so much. Ignore that words, one man can judge you, but a lot of people are saying the same thing. Means not a lot of people, or some people say, I mean, if that is the punctuality meaning, then you must have attend the class by 9 o'clock, and you must have to go through all the PDF and videos. You see, in the case of offline coaching, have you got the recorded videos? I'm telling you, I'm teaching 200% more in the online than the offline. 200%. You please refer to my previous notes. I hope some of my students would be there taking now also, those who have been taking the coaching last year. So some of the students, I mean, this year itself have taught in the Tirupati also, the recent batch. So you please look over the notes of that and you please look over these notes, how much information I am giving you, how many examples I am taking you. Mr. Sivia.Asin, would you please say fifth question, effective stress? No, I don't say any question because that I have given you assignment. So the meaning of assignment means you have to apply that. I will give you the solution later. Sir, in reality, it is possible to decrease dam width. Yes, I said to you, Mr. Anonymous attendee, it is possible to reduce the dam width before construction, not after construction. For ESC theory is important, Mr. Anvesh, and I'm giving you enough theory over here. It's fine. Whatever the note points I'm giving you, it is fine. Sir, I did not get the answer for question that why delta Q in anisotropic is same and isotropic soils, delta Q same. See, in the case of anisotropic soil, I told you clearly, you observe. In order to apply the flow net characteristics, what is the meaning of flow net characteristics? You see, the person who is asking that one, in order to apply the flow net characteristics, equation should convert from anisotropic to equivalent isotropic. Once I convert into equivalent isotropic, what are the flow net characteristics? So this is one of the flow net characteristics, right? According to flow net characteristic, flow rate passing through any two successive flow channels are going to be seen. So once I convert this equivalent nature, means anisotropic to equivalent isotropic, then I can apply all the characteristics of the isotropic, which means flow rate is same. So in gate question we have taken NF and -1. See, they have given number of flow lines. When they give number of flow lines, you have to take number of flow channels as a -1, means number of flow lines -1. Mr. Nimesh Patel. Factor of safety in this chapter and last chapter is same, and why we are having a higher value of factor of safety in last chapter. I did not say any higher value. Earlier I said factor of safety greater than 1 is safe, but now I said the range 4 to 5. I really admire you, sir. Thank you so much. Thank you, Kaushik. Thank you, Sachin, Shankar. Mr. Parameshwar, teaching is super, but give break 30 minutes, sir, please. Already our session is half a day session, so if I give you 30 minutes of break, we cannot go further. So I can give you 15 to 20 minutes, so max of 20 minutes. Mr. Sai Krishna Aditya, sir, in chapter number 6 assignment for 5th question, the answer is I am getting 39 centimeters per second. I look into that, Aditya, but I hope that the answer is whatever answer I am providing you is correct answer, but I'll look over that for you. Sir, when shall we complete the geotechnical part and start foundation? Because I started refer RCC structures. Will please give an idea. It will be taking now it is today 14. Possibly by 20th we can start the foundation engineering. Possibly by 20 or 21st we'll be able to start. Right? I cannot say as directly because I'm taking time. So fine. So the taper edge at the base of the dam is provided for exit flow field only. No, see that depends on it. It's not, see, if you observe this flow field over here, whatever the profile I have provided over here, this is different, right? So that is going to be like, it depends upon the type of conditions they give. You don't need to worry about that whether it's a taper edge or whether it is going to be inclined or something else. They will give you the length of the seabase, then you can find out the answers. So with this, I'm leaving the today's session. It's already been 1:50. So tomorrow I'm going to discuss that. So is delta is our assumption or is property? See, I told you flow is a study. You please look over the first assumption I made. The assumption is flow is a study. So discharge remains same. That's an assumption, my dear anonymous attendee. So while solving, I'm getting the approximate answers which were given by you, but not exact answers. See, I gave you ranges also. If your answer is in between the range, Mr. Bhuvan, you can get down the correct answers. Can you provide the IES syllabus? I have provided the IES syllabus at the starting of this class also. You please go through that. So now, as of now, today I'm leaving. So we'll be discussing tomorrow.